IO, I realized I said maybe I'll try and start streaming a little bit earlier today. Maybe noonish EST, because, you know, tomorrow's workday and whatnot. And now it's 2:30. So, yeah. We'll see how mega these mega streams are. Let me get my chat situated. Hold, and then I will describe where we are at again. There we go. Okay, sorry, that took way too much. Hey, Wereworm, did your work thingy happen? For those who weren't on the stream, I mean, it's probably just me and Wereworm watching, and you know, involved in this stream right now, but I was to understand that Wereworm got 2 hours of sleep last night. Oh, no, we have an Adam here. Good to see you, Adam. Thanks for dropping in. Wereworm says, I am just in from work, so go to bed. I appreciate having you here, but, like, Jesus, man. Oh, boy. Red Bull in the beard. I appreciate it. You do whatever you want to do. It's your life, but woof. I would go to bed. I'm allowing it. Okay, let's get spun up here. So, the other day, we got this lil board going. So this EEPROM used to just be in the Super Mario Brothers cartridge, but because of the way that was hooked up, we couldn't close the cartridge and button things up nicely for the show next weekend that I'm taking this to. So, this needed to be done anyway. And we got we proved that the EEPROM itself being moved over here is working fine. In fact, it should work right now. Let's see. I think when I just glanced at it, it looked like it was connected directly to the chip select in the way that it was working before. Or maybe it just doesn't. Sorry, checking. Yeah, it looks like chip select is connected directly. Maybe it's just spurious. So this goes to, the thing is, floppy drive controller. This is what we're going to try and make work here. We're going to try and access this floppy drive controller and then try and make that floppy drive controller actually drive a floppy. But to do that, we are going to have to do some address decoding so that at certain addresses we don't access the EEPROM. We instead use the gal to say, oh, at these addresses you are going to activate this thingy instead. Oh, you know what's a stupid thought? You know what? No, that is a stupid thought. I was going to say something about maybe this thing being on the data bus was screwing things up because its select lines hadn't been set up, but it doesn't, it's not connected to any of the buses yet. So that would be fascinating. Anyway, Wereworm says, you forgot to put the tweezers on top. A good point. A very good point. So I'm wondering if just because the wires are so freaking long, that is causing this to kind of be spurious. Because what we found the other day was introducing this gal to do some address decoding, and then just taking the chip select signal for the EEPROM and just running it straight through this gal and not doing anything to it except for just like passing the signal from one side of the gal, you know, from an input of the gal to the output, made it to stop working. But right now things are wired up. The chip select is wired directly to the chip select on a cart, and it's not working. So maybe that means it's just spurious, and maybe it's that these wires are so long, like they're long enough that there are interference problems being introduced that are causing it to not work most of the time. Totally possible. Yeah, because now it's like just not happening at all. Let me see. Well, I guess the only way to be sure at this point is... I mean, I could put the logic analyzer on it. I could. But it strikes... it feels to me that it shouldn't be... I'm trying to decide if I just want to go in here and cut down these cables and resolder them. And Wareworm says, only one thin wire for power and ground. That is also true, but, like, I've never really had a problem with that. Like, I've never had thin power buses, like, make things not work. They will heat, and they are not, you know, great for a nice finished product, but I've never had it just not cause things to not work at all. Let me do a quick double check here. I don't know why they would be, but there are a couple pins that look like they might be bridged. They're probably not, but while this iron is heating up, might as well. Get ready to make beeps. Get ready to do it. Okay, so firstly, let's just check continuity between... Chip select hooked up just fine. But it looks like maybe ground could possibly be touching this pin. Nope, not even a little bit. So could it just be this big old loop causing noise to happen? Let's start with that, because if it's right on the edge with these cables, and I shorten this up and it works more reliably, that's a good sign. And that is a thing I can do very quickly. Because, you know, at a certain point, wires become antennas. Also, I don't have good decoupling capacitors really around, which... There's a decoupling capacitor for the Floppy IC that I put on there quite a while ago, but that could also potentially help. Where is my... Here. Yeah. Wareworm said, check 5 volts on the board and add magic bypass caps. I'll check again, but the 5 volts has seemed solid. I checked it last night. And it was, again, when I had chip select directly connected like this, it was working what looked like fine, but maybe it was just, you know, marginal. But again, here's another big theme for this build is I'm trying not to let myself get sucked into wild goose chases. Gotta try and do my best. No, still screwed. So it's hard to tell. Is it the length of the cable? Is it the cartridge just not being plugged in very well? Is it? It can be so many things. We checked last night for, you know, the obvious, like, shorts and whatnot. Things seem, continuity-wise, everything seems perfectly fine. Nothing seems like it's bridged too bad or anything. Everything looks okay. Yeah, this is fascinating. That, as of this morning, it's just not working at all. When it was working the other day. If we do it enough, will it eventually work? Huh? 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 No. It won't. Just making sure I actually have my things plugged in the right way around. Oh, wait. I was hoping I had a broken wire. No such luck. Everything is connected just fine. Because this header situation seems like a highly potential weak link for this whole thing, but everything looks fine, I think. Is it time to just clip the logic analyzer to here? let's start by just seeing if the logic analyzer will clip to this chip in the ZIF socket in the first place, because I had troubles before. But that was with a narrow chip, and I think really that was the problem, was that it was a narrow chip. Not so much that it was in a socket, really being the issue. Yeah, I think that's gonna work just fine. And then we can just like do some sampling on, I guess, chip select itself. See what the signals look like? Sure. All right, let us, I guess I'll keep using pod 2 and take off some of these things. And I'm just gonna move this off screen for a second. Werewolf said, the 11th commandment, thou shalt check thy voltages. Yeah. Okay, so, actually going to move this up a touch, such that my bottommost pins line up with the bottommost pins, because the first thing I need to attach is ground, and that is over here. And then, one of the things that makes these nice is that now I can just attach all of these wires to the clip, and like I don't have to fuss around with much. I just clip onto the thing and I sample, and that's it. So let me look at the pinout of this EEPROM again. For starters, I'm just going to look at, I mean, I guess I'm going to look at chip select just to make sure it, happens. I mean, surely it is, but let's just start there. Where is my PDF? It is over here. Sorry, I know you can't see it. I know. Okay, so yes, ground is over here, and then chip enable is on 22, and this is 17. So 17, 18, 19, 20, 21, 22. Let's just start there. Let's see, over to that one. The logic analyzer with very poor labeling. Sorry, best I can do. So let us adjust the format on this thing, and we will change. I mean, I'm not using clock for anything, and then no count, no latch. That is nothing. Totally different piece of hardware now. So let's make one for, I mean, I guess right now it's just going to be, the only thing we have plugged in is pin 0 is, yeah, I know you can't see my face, sorry. Pin 0 is chip select. Yeah. Pin 0 of pod 2. And that is modify label. Chip select. Done. Okay, now we have to change the trigger. And let's see, trigger on A greater than 1 microsecond. And that's going to be it going low, because it's an active low signal. Who would have thunk it? And I'm just going to run it, and the whole thing is off, so of course it's going to sample it right away. But if we apply power to this thing, I think it's reading bad instructions and just doing the break interrupt over and over and over again. So I think, interesting. It just stays low. This is on, right? This is on. Interesting. So chip select should be high pretty much all the time. But according to my probing, it's low. Let me literally just use a multimeter to confirm this. That it is in fact just at 0 volts. maybe something is not connected properly. Alright. Give me a ground. Well, I'll just use this ground as well. So, 17, 16, 15, 14, 13... Wow, no. 17, 18, 19, 20, 21, 22. Oh yeah. That's ground, for sure. Huh. Why is that ground, yo? That should not be ground. Like, even if the chip is getting selected all the time, shouldn't be ground, because it is, the cycle of reading from memory would cause it to toggle every cycle, even if it was being accessed every cycle. So that ain't right. For the sake of Wereworm, I will double check mine voltages. So ground should be there, power should be there, and oh wait, no, that's totally the wrong pin. 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32. Interesting. That is reading as a pretty low. Let's see, what scale is that on? Oh yeah, that is coming up really low. That's coming up as like a volt. Interesting. And that should be the same on the connector. Yep, same situation on the connector. Interesting. Wereworm, I owe you an apology. Huh. So that's a thing, huh? Why would that happen? And how do you resolve it? Do I do it by adding bypass caps? I'm out of my element now. I really am. Is it because I wired in this big chonker IC and now it's really screwing things up? You know what is a relatively easy way that I can check that is disconnect the Nintendo, pull out these headers, and jam 5 volts into this from another source. More directly. And if it looks more betterer, then it's something about this whole cable setup. So, what's my best way to do this? Alligator clips and find a... I have a big chonky 5 volt. Oh, that is right behind my face. I have a big chonky 5 volt bus right here, so let's just shoop onto that. And I will plug that into something. Maybe one of these Pi Picos. One of these has to work, right? Some of these I have blown out the 3.3 volt regulators on, but not this one, so that should be usable. Let me get a USB. Just kind of put that over to be prepared. And then get some wires. That one is all messed up. How on earth would something like that happen? Oh, I've thrown them all over the place. I need a male to female. All of mine are same gender, both sides that I got sitting over here. Let's check the draw. These are also, of course, ironically, the ones that I never need. And the second you need them, you can't find them. Nope. Yes. Yes! Wereworm said, add a power LED. Also, is it shorting the metal bar on top of the cartridge? No, I've tried to be pretty careful about not touching anything to that bar. Because that was on my mind as well. Okay, so let me review. V bus is the USB bus voltage. Connect that to this alligator clip. And ground. Now, what do I do about ground? Oh, I have that chonky ground bus as well. Over here on the floppy connector. Is that connected? That seems connected-ish. Is it shorting on anything? No, I don't think so. Okay, and alligator clip 2. Wire and wire 2. Raspberry Pi Pico ground. And see what we get when we run this directly off of USB power. Get my probe ready for probing. And it's on 10-volt scale. And ground. And 5 volts. And that is 5 volts. Like on the money. So it's not this board in and of itself that is screwing something up. There aren't like any weird shorts or something on this board. When you feed a good 5 volts into it, you get 5 volts. Okay, so let me do the same thing on the other side here and see if I just power this on and check the 5 volt and ground pins without the board plugged in, what do I get? Because it could also just be that, like, you know, this power supply can't drive this much shit. Which would be mildly surprising. Because, like, you'd think this thing is built to, like, hang peripherals off of and stuff, but I don't know. I do not know. Might need... Like, if we have to do a situation with, like, an auxiliary power supply or something, that's not really so bad. Okay, I guess I can just reuse these guys. Alligator clip to positive lead. Alligator clip to positive lead. Alligator clip. Alligator clip. Alligator clip to positive lead. And then this goes to the positive pin, which is the one opposite pin 1. This is pin 1. Therefore, this is the one opposite pin 1. Some might call it pin 32. I think that's pretentious. And then ground is the last pin on the pin 1 side. And alligator clip to lead negative. There you are. And no. See, this is the thing. These I don't know if you saw that, but as soon as I tried to plug this in, it shoved the and now I've broken the wire. See how I said this is like the weakest link in this situation? Yeah. I should definitely put some hot snot on this, or something. But for now, I'm just going to solder it back together. And burn myself lightly in the process. I owned this pair of helping hands. I did buy one. I bought it from Radio Shack when Radio Shack was going out of business. As far as I know, I didn't like toss them out or anything, but I have no idea what ever happened to them. Because I would totally use them. But also, I keep not buying a pair, partially because I'm like, I know I've got a pair somewhere around here, and as soon as I go buy a new pair, I'll find the old pair, and that will have been a wasted, $10 or whatever. Woe is me. Okay, I just want to make sure that one is good and connected. Because that is the ground pin, and, you kind of want that to be connected pretty good, is my understanding. Okay, so if I turn this on, this will just shoot up to 5 volts. No! Fascinating. It's still, yeah, see, it's like doing 1 volt. Adam said, do you like having 10 viewers? Yeah, man! I really do. Okay, so that's fascinating. Does it all come back to my power connection being really fucked up over here? Am I not sending enough current into the power supply? And that's screwing things up? I could see that being a thing. But you'd think it'd just turn on or not, right? I don't know. I should really fix the power supply brick. Oh, yeah, see? Interesting. Maybe it is related to the power supply brick. I think it's related to the power supply brick. See, look at that shit. Now it's 5 volts. Every time. Cliff Janey said, we still have Radio Shack in Cairo, but they don't carry all the small parts anymore. I'm amazed they exist at all. What do they do at this point? Just sell cell phones? I mean, I don't know what else they would be doing at this point. Okay. It would be nice to be able to take apart this brick, because the issue is there's like a fault in this wire. Do I have... Okay, so this is... My alternative is to find another... Okay, it's DC 10 volts. Yeah. This is funny. I lived in Japan for a little bit and didn't learn Japanese very well at the time and then felt bad about it, so I've been working on my Japanese for the last couple of years. And it's always funny when like suddenly I'm like, I can read stuff. Right here, in text that you can't read, this little text right there, it says, for use with toys. That's fun. Let's see. 使用しないときはコンセントから必ず抜いてください. When I started that, I thought, okay, so this first bit, 使用しないとき, is when not in use, or when not using. And then it says consento, which is in katakana, and is it consent? It's a foreign loan word, probably. And so it's consento kara. And kara means from. Consento kara. From consent? And then I just run into kanarazu is a word that I know I should know, and I don't, so yeah, it's, and then nuite kudasai. Is it please disconnect? Nugu is to, no, nugu is like to take off shoes. Or is it to get undressed in general? I don't know. But that would be nuide. So nuite would be the verb nuku, and I don't know what the verb nuku is. So yeah, I can read the first phrase. Anyway, moving on. So it's, I would vote that it is definitely a problem with this, and maybe we should fix it. But I don't know how to open this dang thing. It's got weirdo screws, and they're probably torqued in pretty good. And I could also alternatively find a 10 volt supply. This thing might be able to take, might be able to take 12. But I can't say safely that that is the case. Does it say what it takes? Okay. Yeah. It says rating AC 9 volts. Well, you know, AC 9 volts, 850 milliamps. The barrel connectors probably don't work, but you know what's 9 volts? Guitar pedals, BRB. Wait, shit. It was AC 9 volts or was it DC 9 volts? AC 9 volts. That's fun. I wonder if you can feed it DC 9 volts and, I mean, that should go straight through the rectifier, right? Like, that shouldn't be a problem. I would think. Okay, this is 9 volts, 1700 milliamps. That should be okay, but will it plug into it? And does it have, well, actually, I was going to say, does it have the right polarity, but that shouldn't matter because it would be going through a rectifier anyway. But, of course, it probably won't have the right size barrel connector. Oh my god, it has the right size barrel connector. You think this'll work? Taco Man says, not gonna lie, I run my NES for some time on 12-volt power supply. That didn't last long, though. Because you switched to using a proper power supply, or because you killed it? Anyway. That totally works. That totally works fine. Oh. Damn it. Maybe it's not the power supply then. Maybe it's something weird about this connection, because it's still showing a volt. Oh, wait. Yeah. Yup. It's a bad connection here, for sure. Do you see this? Oh, I wonder if it's like yeah, it's got to be a bad connection on the cartridge slot. Do you see that wiggling around right here? Well, there's your problem. I bet it's not related to the gal at all. It's because the contacts aren't in there very good. Which is the original thing that I was playing with. That's fun. Well, solved that. Yeah, I bet you money I plug this back in now that I have jostled it around and we're getting a proper 5 volts, and it will be fine. Bet you money. Bet you dollar bills. And then I'm going to read some chat, because there has been some chat. There has been activity in the chat quadrant. Oh, I guess we should bring the Nintendo window over here, huh? Hi! Look at that working. Okay. Well, now I guess back to trying to run it through the gal and seeing if it works just fine. So yes, it's just the cartridge not being plugged in very well. Well, that's nice. Would be cool probably to have some wires hooked up to the 5-volt bus just so that like I can monitor it and see if the connection is bad so I'm not going crazy. Maybe. At a later time. Okay, let's review chat a little bit, and then we'll run things back through this gal, and then we'll get back to trying to do address decoding, and then we'll hook up this floppy drive controller to the address and data buses and see how much it screws up. Taco Man said, when my local Radio Shack was closing, I bought all the Arduino stock they had on the cheap. Yeah, the stock hadn't gotten cheap enough to buy like proper Arduinos, but I bought a bunch of like Seed Studio shields, which is funny because I didn't have any like actual Arduinos. But I figured, well, these are stupid cheap, and I could probably steal a bunch of the components off of them, and I have. That has actually turned out pretty good. The two things that I haven't played with that I really need to are I have a shield with a Ethernet controller on it. It's probably an SPI Ethernet controller, and I would love to connect that up to something. And I have never used it. And I also have a nice, probably also SPI LCD screen that, again, I haven't really thought of a project for it, but like it's just sitting there being beautiful. Adam said, well, I get my first Arduino in last of this month, and this is the best place to buy Arduino parts is eBay. eBay's pretty good. You can also get like Amazon. I keep saying I feel weird about Amazon, but like especially Arduino stuff, Raspberry Pi Pico stuff, you can get like it's very accessible on Amazon. Cliff Cheney said they sell this is about Radio Shack. They sell non-distinct random electronics. Their international supply chain died. Yeah, I'd imagine. So those are probably like franchise holdout Radio Shacks then, I would imagine. Because there's actually like the next town over here, I have to check to see if they finally died, but there was a franchise Radio Shack, and at least as of a couple years ago, they were still running, and I forgot about them actually entirely. I should check again. Taco Man, the 12-volt supply thing. Cliff Cheney said, Cairo has some awesome hacker malls, just floors of used equipment. I often search them for unique items. I miss in Japan. I assume they're still prevalent, but of course they're not going to have the same stuff that they did back in the day. They used to have, I mean, they probably still do have, but I used to go when I lived there for the year that I lived there in, it was 2015, 2016. They have junk shops where it's literally like you go in there and it's just like rows of maybe it works, maybe it doesn't, but there's no RAM or hard drive in this thing, like computer chassis and stuff, going for, like selling for pennies on the dollar. And you just go in there and you like grab some stuff. I got at least one Power Mac G3, blue and white, there at one, and I think it had RAM and was just missing a hard drive, and I put a hard drive in it and jiggled with it a little bit, and it worked perfectly. And that was my first OS X machine that I ever owned, and it was awesome. And then, yeah, lots of similar stuff. Always ticked me off because they had Octanes. They had a bunch of Octanes there. And of course, well, especially at the time, getting an Octane back up and running would have been a challenge for, teenage me. But just the fact that I looked at them and I was like, oh no, they're like $30. I can't afford that. Because mind you, like, I think that G3 might have been like 20. And again, I was like a teenager, so I didn't have a ton of money at the time. And I was like, oh, maybe they were like $50, the SGIs. And I was like, I don't know, but these look really cool, and never bought one. And I did eventually buy an Octane, and then sold an Octane. But I always think about what could have been $50 Octanes. Not in guaranteed working condition, but still. Taco Man says I killed it as far as that power supply. Taco Man said, check with the game and see if it works. If not, then it's a bad connection. Turns out it's a bad connection. Adam says more about parts on eBay, so. Wareworm said, add a power LED. Taco Man said, I still got the Ethernet shield on the box. Don't know what to do with it. Yeah, I'm the same thing. Like, I just want to do it because I really want to build like a hardware Ethernet card. You know what I mean? Build an Ethernet controller with 74 series logic or something similar. I think that would be fun. But I don't know what I'm actually going to do with this SPI Ethernet thing. Francois Reval says, plop. Francois Reval says, coming in from the hackerspace, we were discussing retro stuff. Good to see you again, Francois. I hope that was an interesting conversation. Retro stuff is really good. Cliff Cheney says, I have always wanted to go see those places in Tokyo. Cairo seems to get off-lease business tech from Europe. Every so often I find rare items. Yeah, I feel like, that's why I was saying, I feel like if I did go back to the junk shops at some point, if and when I ever go back to Japan, I feel like it's not going to be the same. It's just all going to be you know, used PC equipment. Nothing really interesting anymore. Anyway, so this was working, and I guess that means I should resolder this wire for the gal and see if it is working now. And I'm just going to get rid of this keyboard for a second while trying not to break anything too bad. Seriously, this desk is 8 foot long, I believe. No, this one might be like 7 foot long. The white ones are 8 foot long. But I built this desk, so I should know that it's relatively long. And I have a square foot of working space here, which is nobody's fault but my own. But okay, so going to turn my iron back on. I don't know why I turned it off. Get some wire and rerun this chip select line like it was the other day and see if it wasn't working just because this cartridge doesn't want to be plugged in very good. What was that? 17, 18, 19, 20, 21, 22. What, I have to wait for that iron to be hot. Adam says, do you have a Twitter? It is on my YouTube profile. 17, 18, 19, 20, 21, 22. There we go. Okay, and we already still have one running from the chip select pin here that is coming in from the cartridge. Already going into the gal, so I just need to run another wire back from the gal all the way across back to the chippy dippy doo, and then see if it still works again, and then be done with it, because what's the theme? No more wild goose chases. Precious little time as it is. I don't need to spend it wasted on hardware goose chase. There could stand to be more solder on this pin, so let's do that. Doot. Too long, but whatever, it's fine. Oakley dokley. Let's see if I can find my frickin' Nintendo window again. Is it this one? I think it's that one. No, but how's my voltage? How is that voltage, I ask you? You know what I'm gonna do? Oh, well, actually, I can just probe it. No need to get fancy. Because I bet it went wonky again. I believe ground here, power here. Oh no, that's frustrating. We got 5 volts. We got it just fine. Yeah. Yeah. Okay. Well, now that we've sorted out the power thing at least, and know that that is a thing that could be trouble, back to the logic analyzer, I think. Because this way we can at least see, is chip select getting selected? Is it getting selected slow? Is it getting selected too slow? Is it not getting selected at all? Which is what it was doing before, but just by dint of it not having power. So let's give it another chance. Okay, ground to ground. And channel 0 was the one that I was doing chip select on. And that was 17, 18, 19, 20, 21, 22. 17, 18, 19, 20, 21, 22. And turn this on. And it's not doing anything. Sanity check that. I think it's probably doing a break command over and over and over again because it's reading bad. Hold up. No, okay. Nothing. Don't worry about it. I had a thought, but it was a bad thought. Okay, so that's 5 volts. Just sanity checking that. And let's run a capture on the logic analyzer. Yeah, there we go. So that is activity. It's happening. It is certainly happening. So I think I can make my sample period a little bit shorter because clearly we're getting a ton of cycles here. Sample period, let's make that 10 times smaller. Sample, cool, we still have tons of them, but you can see they're a little more square now because heck, I can knock this down even more. Let's change this to fastest it'll go, that's fine. 4 nanoseconds. Run. Did you capture a sample? Run. What the fuck? Oh, there you are. Okay, so it just caught this very small little sample here. I don't know if you can see that. That little white block. Let me just put it right where you can't see it in the light. Oh, zooming on this thing is a pain in the butt. It always zooms to the middle. Okay, so. I feel like I saw some spurious stuff over here. Yeah, that looks like, like this spurious spike right there. I don't know if I need to be worried about that, but the main thing is we are clearly getting chip select pulses, so it's not like they're not getting them. And those are active low. You know what, actually? Just to make sure I'm not totally insane, I'm also going to instrument the incoming chip select line because those look like, I may be crazy, but I feel like this short pulse, I would expect the short pulse to be like the active pulse, but this is an active low signal. Anyway, let's not get too conspiratorial. I just want to check the incoming signal against the outgoing signal and make sure it's not like getting inverted or something weird. And this will also, because it's on timing mode, so it'll let us check like how delayed from each other they are if there is a significant delay. So, gotta change the format again. Sorry, I'm wobbling the camera around. Let's call this, I don't know, modify label min CSB. So that is CSB from the Nintendo. And we have that on pin 1. Okay, so let's run another capture. And turn that channel on. So they're real close. Like there is clearly a little bit of a delay. The funny thing is the Nintendo signal is noisier. Like that has more spurious clocks on it. But you can see that, can you? Let me not zoom, scoot. Let me scoot this where you can see it. Okay, there you go. So top one is the one that's going to the chip, bottom one is the one that is coming from the Nintendo. And you can see the one from the chip is delayed. Well, you can't really because of this light. There we go. You can see that this one, the top one, is slightly delayed from the bottom one. That doesn't strike me as like that it should be enough with how long that is to really mess things up. Like, that's got to be... Okay, so my seconds per division are 50 nanoseconds. Now, I don't know if you can really see the divisions there, but the divisions are... Here's a division, here's a division, here's a division, here's a division, here's a division. So these are pretty much exactly 1, 2, 3, 4 divisions wide, which would be 200 nanoseconds. So this is... I realize that this is not the active part of the cycle, but this is... this high part of the thing is 50 nanoseconds long, and this delay at the beginning is like maybe a quarter of a division-ish. So that would be like 12 to 20 nanoseconds out of 200. So it's a 10% difference. But maybe that could be screwing things up? Maybe? Anybody think that's screwing things up? And how would I deal with that? I just feel like it shouldn't screw things up that bad. Let me read chat, because, Yo Megaton. Wereworm says, what was the change? Simply adding a connection from chip enable to GAL input, or passing it through the GAL to the ROM? Passing it through the GAL to the ROM. So there was already a chip enable connected here, and now I've just, instead of connecting the chip enable directly from the cable to the chip, it's going from the cable to the GAL, then getting passed straight through, and then going to the chip. Yeah, maybe GAL slightly too slow, but there is clearly some delay, but operating systems for the Arduino. Cliff Janey says, what OS is the logic analyzer on? Oh, Cliff. Oh, Cliff. This is HP custom software, man. This is a logic analyzer from like the late 80s. That probably cost like $1,500 when it was new. It's running some custom HP software. Running on some weird CPU. It's not like a modern x86 logic analyzer box. Wereworm said, yeah, but the EEPROM will also be slower. Yes, that is true. It will respond a little bit slower. Oh, boy. Boy. What if we always... What if we swap this around so that chip... Because right now, the way that this EEPROM is set up is... Like, maybe just here's an experiment in case things are slow. So with EEPROMs, as a note, or with memory devices, like static memory devices in general, it is, you get faster response time out of the chip if you keep the chip enabled at all times, and then only output enable when you want it to write stuff to the bus if it's an output only device. So I might try doing that. So instead of, right now the way it's set up is output enable is grounded and chip enable is connected to chip enable. What if I swap those around? Might make things just a little bit faster, and if that's the problem, you know, solve that problem. Maybe it's worth a try. I can't think of anything else, so let's just do it. And make sure this thing is off! Off! I don't know why I keep unplugging the pins from this. Like, I was just talking about how that's so useful because you can keep it plugged in and then just strap it onto the chip when you want to instrument the thing. But apparently, I don't take my own advice, and that doesn't surprise me the littlest bit. So, let's see, which pin was output enable? That is 24. So, chip enable was this guy, which is 22, 23, 24, and that was going up to... What's the deal there? Sorry. Let me... what? Pin 2 was going to... that. But why? but why? I mean, pin 2 was supposed to go somewhere. Why is it going to pin 24? I kept going back and forth last night when I had sleepy brains trying to figure out if I had this wired up correctly. And now it still seems wrong again. So, pin 2 on... This is the actual EEPROM that's in here. Pin 2 is... Oh, pin 2 is A16. I'm blind. Okay. And that is going to 24 on the header, and 24 is pin 16, because there is... Right, duh. There's no chip enable on the cartridge. Duh. So, that I can ignore. There's nothing on... Well, pin 24 is address pin 16 on there. So, confusing myself. So, on the EEPROM, let's see. This is 1. So this is 17, 18, 19, 20, 21, 22, 23, 24, which is grounded. So instead of grounding this, chip enable on the EEPROM, let's connect it to, or output enable, right? Yes, instead of grounding output enable, I'm going to connect output enable to chip enable. Assuming this wire can stretch far enough. I think it will just make it. And we'll see if this makes a difference. And then I will ground, because I should have never removed this pin from, or this wire from this little ground node here. Whoops. There's really no need for that. Oh well. No harm, no foul. And then we will connect chip enable to ground, so that the chip is always enabled, but it's not outputting anything until it gets selected by the Nintendo. And I don't know if this will make a difference, but we're just gonna see. Okay, let me just make sure that that is reasonably not shorting two things and making reasonably the right connections. Yeah, that is chip select coming out of the gal, going to output enable on the EEPROM, and then let's make sure ground actually connects to, yep, ground is connected okay to. Let me just double check my numbers. Chip enable. And this pin that I was screwing around with, where all the ground leads are coming in, are reasonably disconnected from each other. And going to the header, this ground thing, still grounded. Okay. Doesn't look like any major obvious shorts. I think that's that. Good enough! And then we get a semicolon because the keyboard's not plugged in, but that's fine. Okay, well, there you go. That solved that problem. No wild goose chases. We just do things, and then if they work, it's good. Okay, let's plug in the keyboard for good measure. Now, this brings in questions of the timing vis-a-vis the floppy controller. But what's the other thing I keep saying? We will burn that bridge when we get to it. Let's just do a nice, make sure everything still works, plug the keyboard in, turn it on. Power button's on the Nintendo. Smart guy. Hecky. I keep having my right hand one too far over. Whoops. Hello. Hecky. Hello. I can type, I promise you guys. Cliff Cheney says, semicolon! Wareworm said, maybe the spurious high pulses help to reset sampling the address bus. It may be invalid when CE goes low the first time and is valid after the short high pulse. I doubt it now. Or the pulses are artifacts from floating bus, and add a pull-up and see if the pulses from the NES get cleaned up. I mean, they're getting cleaned up by going through the gal, clearly. I think it's just sampling error from my logic analyzer. I think it's probably, I mean, this thing is so slow, there's probably, you know, transition time going on there that we're not seeing, because a logic analyzer doesn't show you, you know, like the actual voltage that's on there. It's just once it crosses a certain threshold. So when it's getting close, if the transition, if the rise time is pretty low, you would probably see some artifacts like that. So it's probably something like that. But anyway, it's working now, so yeah. What next? Let's go ahead and go back to gal programming then. Wereworm said, how slow is the EEPROM? It should be pretty fast. I haven't looked up the, well, I was going to say I haven't looked up the datasheet, but like, we're looking at the datasheet right here, so let's see. Now, the issue is, this is like a standard, I guess I would assume it would be the same across the board, because this 29EE010 is like a standard EEPROM type, and so I would assume the one that I've got conforms to the standard, but the one I've got, I'm actually not sure what brand it is, but it's not SST. It's just got a logo, and I don't know whose logo that is. But it's a 29EE010, so let's see what this thing says for 444, like AC timing characteristics. Ba-doo-ba-doo. That's operation mode selection. These are currents and voltages. Power up to read. Here we go. Read cycle time, 70 nanoseconds minimum. And that is, well, really what we want to look at is time from chip select to data out, right? Let's see if they actually have the timing diagram on here, because I can't do much without a timing diagram. I just can't. Yes, so you can see there is a delay between chip enable and output enable. This is pretty universal, which is why I figured that would make things speed up a little bit, because if the chip is always selected, the time to output enable disappears, basically. Booty-dooty-dooty-doo. But anyway, the time from, yeah, read cycle, what am I looking for? I am looking for the time that, I guess the time from chip enable to data valid, or really the time from output enable to data valid. Well, either or, let's look at TCE and TOE. Those are the numbers we care about to answer your question. TCE and TOE, chip enable access time, is up to 200 nanoseconds. Oh, that's for VE? We need the EE. EE. TCE, chip enable access time. We were already looking at this. Is maxes out at 70 nanoseconds. So it could make a difference, but again, oh, I wasn't actually looking at the chip select time. I was looking at the opposite, the chip not selected time. I'm not gonna switch the camera, but let's see. 1, 2, 3, 4, 5, 6, 7, 8 divisions of chip select being low, and we're still at 50 nanoseconds per division, so that is a, help me out here, that's just double the previous, is that 400 nanoseconds? Yeah, 8 times 50. 400 nanoseconds. So, sorry, the Nintendo's, it holds CS on that chip low for 400 nanoseconds. So, I mean, sure, maybe that, I mean, clearly that introduced just enough to screw things up, but, seems fine now, but, he says, is there a -70 or something on the EEPROM? Yeah, he said, Wereworm says, should be plenty fast, so, yeah, I don't really know why that weird timing margin thing, but, and it could be that it takes extra time since I have these long-ass cables that, the bus isn't settling as fast too. Might have been screwing things up. But anyway, that seems to have cleared stuff up. might still be a good idea to shorten those wires at some point. Because this thing is running at... I think the Nintendo runs at 4 megahertz, so it's not exactly slow. This is at the point where you actually do have to start worrying about that kind of thing. Like, 1 megahertz, when you're working on like an Apple II or something, you can get away with a lot. This is starting to get to the point where that might actually be causing problems. So between the delay and the bus settling time of all of this wire that it adds, and then also going through the gallows, probably just enough to screw things up. So we might still have to shorten this when I try and get that working. But anyway, where I was going to go here was, let's go back to WinKuppel and let's open the FDC mapper. And one thing that I want to do is, this was just passing it straight through. What I would actually like to do is the ROM chip enable. I really only want it to go low when... oh boy, we really have to think about this. So let's look at the MMC3. So the MMC3 always maps this E000 to FFF is fixed to the last bank on the EEPROM. So actually, well, actually, the way that it mirrors, it doesn't really matter, does it? I don't think it will really matter. We could basically, by having whatever combination of A17 and A18, because those do not get routed to the EEPROM at all, we'll just choose which mirror happens. I'm confusing myself, but I guess what I'm saying is it doesn't really matter how I set A17 and A18, because of stuff. Let's just start with, if A17 and A18 are low. No, that's where I'm confusing myself. So this, it would always map to the second to last bank of the mask ROM, which the mask ROM has A17 and A18. So if it's accessing the second to last bank, second to last bank. Oh no, sorry. This is the one I should be looking at. Last bank. That's why. Then the MMC3 would always be outputting to try and access that bank. Whenever it's trying to access that bank, these would be high. So, to make my E000 to FFF area of the ROM still work properly per what the MMC3 is expecting, I need to enable chip select when A17 and A18 are both high. Yeah, I think so, because it's the last bank on the mask ROM. So let's try that and just see if it works. So this would be, we'd just be muxing it, so it equals it would just be A17 and A18 and chip enable B. So if A17 and A18 aren't both high, then this will wait, no. Oh my god, frickin' active low logic. Because that would really only work for an active high signal, right? Right? Because if A17 is... Yeah, we want it high. So basically not A17 and A18. Right? Yes? This is very easy. I could do a freaking table for this. Let's do a table for this. A17. I don't know where vertical bar is on this freaking keyboard. There we go. A17. A18. Chip enable. So 0, 0, 0, 0, 0, 1, 0, 1, 0, 0. Wait, why am I doing it this way? Oh wait, no. Right, these are my inputs. I need to add ROM CED here. ROM CED. 0, 1, 0. Yeah, we're actually gonna do like frickin'. Is this a Cardinal map? I can't remember. I didn't go to school for this. But I guess it's gonna be sum of products or products of sums or something. However that works. 1, 0, 1, 1, 1. And then what I would expect for outputs. So I want, if A17, I want ROM chip enable to be high in any of the cases that A17 and A18 are not both high. So pretty much everything except for, okay, so it's basically, this is the case right here. This is the case, the only case that I want ROM chip enable to be low, right? Yeah. So really, I guess I can look at it as, so normally what you would do is you would, like, where any of these are 0, you would in your equation put not that input, and then, so it would be not A7, like this line would be transformed to not A17, not A18, not CEB, or not A17, not A18. I wasn't saying ands in there. Sorry. Not A17 and not A18 and not CEB. Or not A17, not A18, not A17 and not A18 and CEB, and so on and so forth. You would do that, oring them all together in all of the cases where you want it to be 1. But I can just invert the whole frickin' thing, and it would just be A17 and A18 and not chip enable B, and then I just invert that whole thing. There we go. And that's how you do that. Don't follow my guide here. That's the way to do it when you just... Remember when we were talking the other night about doing things from first principles? It's the only way I know how to do things. You could simplify this. There's probably a more obvious way to do that, but there you go. If you just can't think it through, there's how to do it from first principles. So, compile. Oh, there is an error. Why you making an error at me? Oh, semicolons. Semicolons. The pain of my life. There we go. Okay, that compiled. Let's program it up. Are we still on? Yes, we are still on GAL programming mode. We're on FDC mapper. And let's make sure the Nintendo is off. Sadly, I don't have, 20-pin ZIF sockets. It's a real shame. Okay. I'm just going to load that again for luck. Program, go. Yay! And if this works right, I should really see no difference. And if you weren't watching last night, the A17 and A18 wires are already connectionulated up over there. Back to the board you go. Seems reasonably plugged in. And cool. Okay, so it still works. My assumptions paid off. Let me check chat for a second. Adam says, what is this programming language? And it is called Kubel. So this program is called WinKubel. I think Kubel is a language that Microchip came up with. These 16V8s used to be, I think, Microchip products, and then Atmel bought them. Might be the other way around. Anyway, it's been around for forever, but it's a hardware description language, like Verilog or VHDL. Yeah, Wareworm said, equations for the PLD. Wareworm said, don't you want the ROM to be enabled all the time except for one address range? No, other way around. I want it just to be enabled for one block, just so that everything else can, and so that I have all of the other areas to play around with. There's not a good reason. There's not really. Santiago said not A18 and A17 and CEB. Probably ages before I got there. Thank you, Santiago. You're a smart cookie. Okay, so that worked. So I think the terrifying fact is that means we're at the part where we start hooking up the floppy disk controller. Shit. So, I guess let's start with the Kubel bit, because it should be... Why did I close this file? It's weird. Anyway, really what I want to do is make a... Oh, sorry. Let's make pin 18 FDC chip enable. And the FDC chip enable is going to be the same thing as ROM chip enable, except at a different address. And I'm just going to pick one at random. I'm going to pick not A17. I put these in parentheses because paranoia. Not A17 and not A18 and not CEB. Which, if I apply the laws to it, that does this just become A17 or A18 or CEB? It totally does, doesn't it? Yeah, it totally does. But I'm not going to do that right now. Okay, and that should basically be it. So what I am doing is saying the floppy disk controller is going to be selected when A17 and A18 are 0, and then it's going to be mirrored a bajillion times across that space, and we are just going to use the low 3 address lines to control the low 3 address lines that go into it, because it has several registers that you can access. So it's basically going to be those 3 registers mirrored a bajillion times across like 128K of memory space over and over and over again. And then hopefully I can just map one of the MMC3 banks to, like the lowest area of that ROM and access them that way. Would be what I would think I would want to do. So, maybe let's start with, I will program this Kubel code to the gal, and then the big question here is I need to do that MMC3 mapping and make sure that's right. So, let's pop this out, program it, and then I will instrument it with the logic analyzer, and we will write a program that sets up the MMC3 the way I think it's supposed to work, and then just loop constantly reading or writing or whatever from the location where I think this should be getting mapped, and see if we actually see the chip enable. Whoops. See the chip enable line for the floppy disk controller toggling at all. Okay, yeah, so this was done. So save it. Compile it. There is an error. Why? Oh, because I defined this twice. This is supposed to be FDCCEB. You can't see. I just mislabeled one of my equations. Compile. Okay, cool. That one worked. I guess I might as well let you see this window. Why not? And program it. Load. Mapper. Program. Program. Yay, done. Okay, so that's that part. Now, I guess I'll go ahead and plug that back in. And let's write a little code. Let me look again at the MMC3 documentation. Okay, so we have several banks. So we've got the one from 8000 to 9FFF, which is an 8 kilobyte switchable program run bank. And let's just map that to 0. Oh, wait, right, this is weird. You can do like an either or thing with these. Never mind, let's use this one. So this one is our fixed one that our code is always running out of. This one is also always switchable. Let's use this one. So my registers, I want them to show up at 1000. And let me re-review how you do that. So I write to this bank select register at 8000, which still confuses me because you can also map program ROM at 8000, but whatever. This confused me in the past. But I want to set R7, and I think if I set R7, I have been setting these to 0 when I've been doing MMC stuff in the past, so I think we will just write 7 to the bank select register, and then write, let's see, this is saying some stuff that I don't care, and then I think just write 0. I think we just write 0 to the bank data register. So, okay, so our code is going to write 7 to 8000 to select that register, and then 0 to 8001, and that should map, I think, this 8000 to BFFF bank to the mask ROM memory area of, starting at 0 on the mask ROM virtual memory space. It's fun dealing with multiple layers of bank switched memory here. Okay. I guess let's just do that. And then we will repeatedly read from 8000 and see what shows up on the scope. And that will involve not doing our keyboard loop. Where is my main core loop? This is setup stuff. Doodly-doo. Enable rendering. MMC vertical mirroring. And init keyboard, and this is our key printing loop. Cool. So instead of that, I'll leave that halt loop code, but let us, prior to that, we will insert this testing thingy, and we will say map MMC3 8000 bank to mask ROM area 0. And that should be as easy as load A as described. 07 store A to 8000. Let me double check my other MMC3 code just to make sure that's not crazy. Where do I set it? Yeah. So register select 8000. Yeah, it is that easy. So select register 7 and then store 0 to it to 8001, and I think that should be it. And now let's do a test. Let's do this in caps so I remember it. Test loop writing to FDC address area. Area. I need to scream it. So let's say FDC test loop, and literally just, I guess the easiest way is load A from 8000. And then here. Well, branch clear carry, as always, branch carry clear to FDC test loop. Very good. And build it. This is always the slowest the first time around. I don't really know why. It takes a long time. Okay, and then let's just make sure it's not totally screwed up. Before I put it on the hardware. Cool. That's pretty much what it should do, is it should print the to the left message and then sit there, and it's going to be spinning, writing, or rather reading from 8000. It's going to be reading nothing, but that should be asserting the chip select line there, if all of the logic is right. So let's program that up. Switch back to, I should really figure out how to use the my favorites thing, but 29EE010. Yes. And load offset 1000. Not FDC mapper.jed. That would be bad. Basic.bin. Okay. Nope. I don't want to erase it. I mean, I do want to erase it, but I want to do more than erase it. Okay, program, and now, let's do this, because I think this is the first time we've had a chance to do this since we have put this in the ZIF socket. Wereworm asks a good question, but what about the write signal? Where will it come from? Very good question, and you kind of answered your own question, but I was thinking about that earlier, because of course the MapROM socket, the MapROM footprint, doesn't have, it has chip select, which is functionally the read signal, but it doesn't have a write signal. So yeah, I think I'm going to have to run another wire. I might have to run another couple wires. I was thinking I might just go ahead and add like another auxiliary header just for extra stuff that I've already, I'm sure I have forgotten and will need to pull from the like main bus proper. So I might just do like a 5 or 10 wide header and probably not end up using all of them, but at least run a few things. Anyway, write this program. Roted. And we pop it out of this ZIF. Woo! And we pop it into this ZIF, which even though it's a little wonky, it works just fine. Because I fucked up some of the wipers, but they work just fine. And for starters, starts up. Everything works okay. Cool. Let's attach some stuff to this thing. I guess I can kind of use what I was already using. Let's put the clip back on. eeprom, because that's one of the easiest ways to gain access to some majority of the signals. And that gives me ground, which is nice to have. And then, let's see. So 0 was, well, really, so 0 was set to the incoming chip enable or something. It's set to one of them. No, it's the outgoing chip enable for the eeprom. But if I just attach it to pin 18, which should be chip enable for the floppy disk controller area, we should hopefully see that doing some toggling. And go. Sorry, I know this one is terrible. It's just awful. And it's always low. Interesting. Chip select coming in from the Nintendo is toggling. Chip select. Oh, I might be using the wrong one. I think that is actually the way I have this wired up. That's the one I care about. And they look pretty spaced out, which I would expect from, you know, not being from program execution directly, but from being accessed from within a program loop. Would make that look like that. Yeah. I guess, yeah, that's definitely, I plugged 1 in when I meant to plug 0 in. Probe-wise. Come on. I don't even really know why I'm doing this. That's definitely the case. It worked fine, but boop. There you go. It's funny that looks, you know, different now. Huh. But oh, because I attached the wrong thing. Damn it. I attached pin 19. The floppy disk chip select is pinned 18. You foolish man. Let's do that one more time. There you go. That's what I'm saying. So those are definitely happening, and they're spaced further apart because, of course, our program loop is accessing ROM, reading instructions from ROM, and then finally getting to the instruction where it reads from the floppy disk controller and then does it, gives a chip select, and then moves on and has to do that loop again. So that's why they're spaced more apart, so that makes me feel good. So, it works. It works. Francois Raval says, gotta go, bye. Wereworm said, it would have been smart to only use every other line on the ribbon. Better mechanical stability on the pin header, option to run ground on every other wire, and space wire if needed. As always, you're not wrong. You're not wrong. Okay, let me drink some water, and then, I mean, we're just chugging along. I think next step is just wire up data bus and chip select and the low 3 address pins and see if we can maybe read some sensible values out of. Hope that this is fast enough that it doesn't have similar delay issues to the eeprom, and try and read some sensible values from the registers. And if we can read sensible values from the registers, then after that it will be time to find a power supply with 12 volts on it somewhere, and grab a floppy drive from around here that's surely somewhere, and plug it into this damn thing, and like try and turn on the motor or something. That would be big. But let's just start at clearing up this area. Wereworm said, just a suggestion for later version 2. Yes, yes, indeed. We have many floating ideas from Wereworm on version 2. He's always thinking for us. Keyboard out the way. Oh, which feels nice, because, I mean, having that little PCB built now. I was saying this earlier, but it's just, I can't get over it. Feels nice that I can just pick up the thing and put it away. Where is this thing? It's here. Where is the butt of it? It's, what? I need this. I'm prematurely over cleaning up. Okay, unplugging the header, because I think I will need the physical access to this card. A little bit more flexible-ish. Yes, so for now, right, because you are going back to that thing about, you know, right not being hooked up and whatnot. Yeah, that's an important signal. And so I guess I will see what I can do about, for right now, just always have read asserted, and just read from some registers, and then we will see about writing. And I will run that thing, as I was saying. Okay. What do I want to do? I want to look at the data sheet for this chip, which I had up somewhere. Was it this one? for super dense floppies, or was this the programming guide? This was the programming guide. This is the data sheet proper. Okay. So, on the back of this thing, let's zoom in. Zoom in, zoom in, zoom in, zoom in, zoom in, zoom in. So, for now, let us... I think the only things we need to hook up are these data bus ones. Won't be connecting the interrupt up to anything. We're just going to do polling for right now. Where are... my... Okay, here we go. There's chip select. That's on pin 6. And then A0, A1, and A2 are over here. And what else do I care about? Oh, read and write. So I think I'm not very good with 8080 bus, 8086 bus type stuff. 8088. I don't know. I think they're all the same bus family, but they're the ones that use the separate read and write signals. The 6502 doesn't have those, but you can derive them. But anyhow, yeah, I think for right now, let me just ground read and connect write to power. Yeah, let's start there. How is this orientated? Okay, so those are somewhere over here. I haven't dealt with one of these PLCCs in a hot minute. You eventually get good at this counting, but they stagger, so it's really hard to see this stuff, but there's 2 rows of connections on the underside of this PLCC socket. You can see them better here. So you can see these 2 rows side by side, and they do numbering like 1, 2, 3, 4, 5, 6, 7, 8, like going across that way. And when you work with them for a minute, you get really used to that counting, and then I have already forgotten. So regardless, those ones that we were looking at are over here. And let's see if I can just smart this out based on what's plugged into what. So VCC is going on here. And if I can't, so if I say, let's see, that's at pin 68. And lower pins are this way. They're also weird because, so they go around, let's see, pin 1 is in the middle here, and they go around counterclockwise on the other side, but, clockwise here. And they go from 1 around to, this is a 68-pin PLCC. Pin 68 is over here. So it's not like pin 1 is here or something. It starts here and ends here, which I always thought was weird. Wareworm said, do you have an estimate at what rate the bytes will come out, go into the controller? Will the NES be fast enough? I am pretty sure, I will double check in this data sheet, but last I was looking at this, there is like a 512 byte buffer memory inside of this controller chip. So you actually basically you instruct it to seek to whatever track, and I think you tell it, now read the nth sector off of head 0 or 1, and then it will, on its own, wait for that sector to come around, read it, decode it, stash it into its internal buffer, and then you can, if you have it set up to DMA, it'll just at that point trigger the DMA and transfer the stuff from the buffer over into memory and then do it again for the next sector. But yeah, I believe it works that way. If you want to read a sector, it has a buffer memory in here that it will store it into, and then it will, when you pull it, it will say, oh, I'm done reading that sector, and then you can read it on out. That is my recollection. Mind you, I haven't looked at this since I was looking at using it for the 65816 computer. Yeah. We'll see, but that was my understanding last I looked at it. So, let's start with this temporary oh, right, I need to count to make sure I know where all of my pins are at. So, looking at this, this wire was VCC, and that is the only VCC on the top side of this, on the this side of the chip is 68. So if I count 68, then there is a ground right here. So it's gotta be. The question is that a ground? I don't think that's a ground that's actually connected to ground. I think that's a ground that's connected to some pin that needs to be grounded. Cool. Because there is a ground, but it's several pins over. Unless it is, wait, 68, 67, 66, 65. Oh, yeah, 65 is a ground. Okay, so that's the counting. 68, 67, 65, no. 68, 67, 66, 65. Cool. So therefore, if I was counting forward, it would be 65, 66, 67, 68, 69, 70. No, there is no 70. After 68, it goes back to 1. Whoops. 65, wait, no. Oi, oi, oi. Yeah, 65, 66, 67, 68, 1. 2, 3, 4. Okay. 4 is read. And read, I want to temporarily connect to ground. That was what I was saying, right? Okay, let's try that. Hope and pray. We've gotten this far without like a whole ton of double checking stuff and a minimal amount of logic analyzing. I am confident we can continue in that direction. Okay, there's a wire attached to the read pin, I think. Let's do this again. 65, 66, 67, 68, 69, nope, 68, 1, 2, 3, 4, yeah. That seems... maybe. I'm willing to trust myself on that. And we'll just temporarily tack that onto this big, fat ground bus for the floppy disk controller connection thing. Okay, so now, and I should really look at the timing diagrams to see if it's something more complicated where read or write can't change their state until a certain point in the bus cycle, but too late now. Let's just do it and then double check in a second. But I think just grounding them is probably fine. Or, you know, hardwiring them for the moment, probably fine. And that would mean, so write is on 5, so doing this again. 68, 1, 2, 3, 4, 5. And find a 5-volt thing for that thing, which I have found. Here we are, over here. Steal power from the gal. Because I'm a misogynist, I must steal power from the gal. Okie doke. So I think that's my read and my write. And only now, let's look for a timing diagram. Ugh. Flies. Flies! I would deal with them, but I'm too busy doing this. Let's double check the obvious, just like the description of those pins. Read, write. Read control signal, write control signal. Wow. Wow. Thanks. You have taught me so much. Timing diagrams, surely you have them. Why is this computer a chuggy piece of shit? Is it because I'm streaming? Like, this is a workstation that I am borrowing from a friend. It's not a bad computer. It's probably all virused to hell. Oh, I feel like I'm getting... Oh, here we go. Okay, host read cycles. So it says data won't be available for however long until after read goes low, but does that say anything about whether I can just have read low always? Yeah. Oh, you know what? Wait. So they're saying, I guess the question is, can I assert read before I assert chip select? Because this is saying, here's your time when chip select settles, you have this much time. Oh, let's test this timing. It says if T7 is something like minimum time before read can go low, that will be important. And that will also be, because I might have to steal the CPU clock signal off of the cartridge edge connector as well, because that drive on the 6502, the actual CPU clock cycle drives when like reads and writes happen. Well, let's see what T7 is. Let's see if there's a minimum time on T7. T7, I like that they are numbered and not something nice and descriptive and easy to remember. Address setup to read. Damn, yep. So address setup to read assertion, you must have a minimum of 5 seconds. Or 5 nanoseconds between those two. Which is not much. That's easily achievable. I'm sure that this will hit that no problem. But that's gonna be a thing. So I can't just keep it grounded all the time. I am going to have to, there's a minimum of 5 nanoseconds. So what if, I was gonna say what if I just attach chip select to it, but no, that's not good enough. I could do something silly and very hacky, and we already know the GAL introduces about like something like between 10 and 20 nanoseconds of delay from input to output. 10 is more than 5. What if we just drove read off of, well, no, because we have chip select coming out of there too, but what if we like took the chip select coming out of the GAL, then fed it back into the GAL, and then just pass it straight through, but used that as a delay line basically, and then finally fed it back out to read? Is that insane? Should I just pull the correct signals? Probably. That's the only thing I can think besides just... Well, there's going to need to be a delay regardless. So I might just have to do that either way. Because even if like this gets set up for proper, like once I implement proper read and write, there still needs to be a delay between chip select being asserted and read or write being asserted. Yeah, it's the same thing over here. So T15 is address setup to write assertion, and yet again, that is a minimum of 5 nanoseconds. So, yes. Might just have to do that anyway. Well, definitely gonna have to do that anyway, because there's not really a separate... Basically on a 6502, when a certain edge of the clock cycle happens, that's when your chip select, really it's just chip select, like on a 6502, it just drives chip select. Also read, and there's a single pin that if it's high, you're reading, if it's low, you're writing, or maybe the other way around, and that's it. So like on a like a 8080, 8086, 8088, they have a more complex bus timing that has more phases. So having a delay between asserting chip select and then asserting the write line would be just something that happens on those chips. We have to derive that here, which includes deriving a delay. because we can't just, if we need this delay, we can't just drive it from chip select. And chip select is derived from the clock, so either way, those are the only signals we have. So I'm going to have to delay them regardless. So let me just do that. Let me just do that. And if I have to delay it twice, so be it. But let's, yeah. I certainly have plenty of pins on the CPLD. And I pretty much already have all the inputs I need. So I have a lot of CPL, or not CPLD, GAL. I have a lot of GAL to play around with here still. Wareham said, assuming double density and 500 kilobits per second, round to 50,000 bytes divided by 2, we would need to read-write every 20 microseconds, so sounds doable even with it, without the luxurious FIFO buffer. That would be... saying that's surprising doesn't sound right, because that sounds like I don't believe you. That's interesting. I wouldn't have thought that you could actually keep up with... like an Apple II can keep up, it does everything in software, and it can keep up with the byte stream coming off of the actual floppy head. And that's a 1 megahertz machine, but also those floppies are much lower density, and the bit rate is much lower coming off of the head. So, but this is also what, like 4 times faster, and I don't know how much faster the bit rate of a double density 3.5-inch floppy is versus a 5 1/4 Apple floppy. But the fact that this might be able to, it could theoretically maybe keep up with a double density 3.5-inch floppy, that's surprising to me. Anyway, what am I doing? So, right. So I guess I'm just going to take, so the right line, because at the moment I'm not going to write at all. You know what I should probably just do is just connect them up to the GAL. Because why not? Because right now I can just always assert that the whatever pin is right will just always be high, and that's it right now. Right. And then we can do our weird delay thing with read. But it's programmable logic. Just pick a pin and attach the thing and change it. Not change it in software. Change it in hardware description. Change it on the computer. Don't change your wires around. So I will need to document this, or I will forget in a hot second. But let's see, 19, 18, 17. So pin. Ooh, no, that's wrong. Shit. That's the wrong side of the GAL. That is the input side of the GAL. I need it going to the output side of the GAL. Whoops. Whoops. Try again. Oh, I already stripped that. Nice. Okay, so that was, this is read, making this one right. A little more solder on that. It's looking a little flat. Okay. Nope. Didn't wait for it to cool long enough. Whoops. Too excited. There we go. Now run this over to, let's just put it on output 18. So don't let me forget, output 18 on the GAL is the input to the right signal on the floppy drive controller. I can go shorter on that. Fuck out of here, dude. Okay, right is hooked up. And I'm going to do the same with read instead of just keeping it grounded, which I can't do regardless. We are going to connect this to let's stretch. Now I need a new wire. Damn. We will connect read to pin 17 on the gal. Doody-doody-doo. That was 1, 2, 3, 4. Did you just see me touch the tip of my iron with my bare hand there? That was fun for a second. Okie dokie. So that's that. Write is hooked up to the gal, read is hooked up to the gal. Now the bit that's going to be funky is... oh wait, no. I am already using one of those pins. I just hadn't hooked it up. That one of those pins is the actual chip select for the thingy-madoo. Tweezers. Okay, I just need to move these both down one. Yeah, whoops. Pin 18 was floppy disk controller chip select. Whoops. And then comes the silly bit where one of these inputs I am going to, or one of these outputs, no, one of the inputs I am going to connect to the output for floppy disk chip select. So I'm going to run pin 18, well, so that I don't forget, let me just really quick take pin 18, which is floppy drive chip select, and run it to chip select on the chip. I should really screenshot this pinout so that I can just switch to it without having to scroll through this whole freaking document, because the document is huge. I mean, I've seen bigger, but there's a lot of stuff in here. And I can't remember which page the pinout is on. It keeps escaping me. Oh, by the way. Oh! I might be slightly wrong where we're. It has a 16-byte FIFO. So, still better, but I guess I was wrong about the buffer being that big. Anyway, still, there is a FIFO, so I think that will save us. Fingers crossed. You said it should keep up, so I'm going to trust you. I'm still looking for this pinout. Still looking, still looking, still looking. Where was it? Surely it wasn't this far down the page. It's on page 1. Jesus Christ. Jeebus Creebus. I'm kind of tempted to just hit one of these flies with a soldering iron, but that feels intensely immoral. Not gonna do it. But I want to. I want to. Francois says, which I think means you're back? I don't know. I don't do much of the... For having a YouTube chat, I don't really do the chatting on YouTube thing so much. I know re means something. And it doesn't mean responding. It doesn't mean... oh my god, what is re even... Oh, regarding. Regarding. It means something. So if you're back, that's cool. If you're not, that's also cool. Okay, chip select is 6, so... just keep on keeping on with how we were doing. So that was 1, 2, 3, 4, 5, 6. And over to pin 18 on the gal. Shorter. Okay. So chip select is on chip select, read is on read, write is on write. Now let's make one that runs floppy disk chip select back into itself so that we can use the delay of the gal itself to introduce a delay before the read or write signal is asserted. Let's see, that was 18, right? Yes, it was. And I'm going to put a little more solder on these as well. So it looks like a big blob, and then the chip soaks it up. It soaks it right up. Whoop, 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 whoop. Okay. Let's make sure I don't forget which is which. This is chip select. They both came desoldered. This is 1, 2, 3, 4. Read. Yes. And this was chip select. 1, 2, 3, 4, 5, 6. Yes. Okay. As I was. Let's connect chip select to another input on the gal for delay purposes. Oh boy, let's see if I can trim a wire this short. Or trim strip. Get it, yeah. Pro. Okay, let us apply those to the gal project now before I forget all of that. So, not weather. So pin, let me make sure that is right. Pin 1 is the chip enable coming in, pin 3 is A17, pin 4 is A18, and then pin 5 is going to be where is this key on my keyboard? What on earth? Am I going insane? No, I'm just forgetting how to type. So pin 5, let me call that FDC chip enable B delay. Okay, and then so pin 19 was the ROM chip enable, pin 18 is the floppy drive chip enable, and then pin 17 was that is FDC write. Pin 16 is FDC read. And I'm not going to do anything with those yet. Actually, no, I should. Right now, for the moment, I'm just going to say that FDC write is always not asserted, and FDC read is also, for right now, always not asserted. Cool. So now we've got things that correspond to things, and we can reprogram how this works later, but we're furiously scribbling. Nico says, I got this stream recommended to me randomly, and I love this concept. Soon we'll have GEOS for the NES, maybe. Surely, I feel like there's got to be an NES Kontiki port. I'll have to check. Surely there's Kontiki for everything. Weirworm says, well, what do I know, but 4 megahertz is a quarter of a microsecond, so assume 6 cycles per instruction, worst case. That's 1.5 microseconds. We have about 10 instructions per incoming byte. That sounds believable. So if we're reading it full bore, yeah, sure. Lunathur says, the thumbnail kinda hurts to see. How so? I don't even know what the thumbnails end up being. Nico said, there's a Windows 98 bootleg for the NES, so maybe we could make something out of it. I need to... Can you drop me a link? I don't know if you can drop a link in YouTube chat or if that's disabled. But, Windows... What? I'm not saying you're wrong. I just want to know more about this. I mean, because obviously Windows 98 is not going to run on NES, but it's like a fake Windows 9X GUI for NES, because if so, I need to see that. Alright, so that is kind of our control signals roughly sorted out. We'll probably need to screw with them more later, but that's a start. So now the next bit is, I think all I need to do is connect the data lines and the address lines to the actual chip. I had run, so you can kind of see there's this big fire hose of blue wires. So obviously this was supposed to plug into my 65816 single board computer, but I'm, not going to do that anymore. So actually, I think I will desolder all of those, and I will just go ahead and redo all of these. And these are the address and data lines that are supposed to be going back to the compooper. But I'm not going to connect it to the compooper after all, so get rid of them. We're just enjoying all of those things. Suck it in. Soak it in. That's what I was looking for. Not suck it in. Suck it in is what my wife tells me to do when we go out in public and I'm supposed to look nice. No, she doesn't. We joke here. Okey doke. That's them going. So let's redo. I'm going to do the address lines first because there's only 3 of those, and let's see where they are at. They are on Right, they were right by the ones that I was already doing. Cool. 7, 8, and 10. And those, I'm going to have to double check where they are on the mask ROM. Let's see. A0 is on pin 12. A0, A1, A2, all right next to each other. So, pin 1 of my thingy coming from the mask ROM port here. That makes this 16, which makes sense because that is the ground pin. Goes over here. Oh, you can't see that. Anyway, that's ground. 16, 15, what was 12 right inside? 16, 15, 14, 13, 12. There is my A0. Let me recount that just because I don't trust myself. 16, 15, 14, 13, 12. Cool. There is my A0. So, start by connecting a wire to that thingy. Sixteen, 15, 14, 13, 15, 16, 16, 15, 14, 13, 12. Run it over to whatever that was. Uh-oh, where has my PDF gone? Uh-oh, uh-oh, uh-oh. Oh, it was the one on BitSavers. Right, what did I say for A0? That was pin 7. And pin 7 is, let's do it again. 1, 2, 3, 4, 5, 6, 7. Feels good. That's the one I thought was. Doing this wrong again. 1, 2, 3, 4, 5, 6, 7. No, you gotta trust yourself, man. If you can't trust yourself, who else are you going to trust? I guess the answer would be other people who know what they're doing better. Well, shit. That is on there well and good. More solder. I wish I had 2 right hands. You know what I mean? I actually did always, when I was a kid, I tried to teach myself how to be ambidextrous. I did not keep up with it, but that would be useful. Okay, there we go, A0. Then it just continues. I just have to watch out for, I will hit a ground somewhere in here, let's see. So, A0 was this guy, it was pin 7 and pin 8 is A1. That makes sense, nothing's connected to it. And then I believe it gets weird when it goes around the corner. So we have a ground which matches pin 9. That makes sense. And then I think pin 10 is the next outside one on the other edge. I think. Wait. It would have to. Okay. 7, 8, 9, 10, 11, 12. You can't really see this. Trust me, it's weird. But that feels right to me. 7, 8, 9, 10. So I think 10 is over here. Again, you can't see. It's tiny. But I think this is A2. Regardless, A1 is definitely this one. So that's easy. A1, or no, A0 to A1. I hope that didn't break anything. Just kind of vaguely throw a pair of nail clippers at a bunch of soldered down wires. Hope it doesn't break anything. Okay, where were we? Trim that a touch. And connect it to A8. Theoretically, that is connected. And then I think that that is... Actually, I guess I can check, right? Be safe. I'm fairly certain, but nothing beats actually physically checking. Doot doot, beep 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 beep. Wereworm said, I love PLCC, but I hate the pin counting. Need to print out some underside labels with pin numbers. Yeah. And I can't keep track of stuff, so it throws me for a loop. So pin, this should be pin 10. And this should be pin 10. And yeah, cool. My intuition was correct. Which it better be, because I've done this many times before. It's not my first time doing this. So you'd think I'd know what I'm doing. Okay, that was A0, A1. Here's A dose. That seems like a thing that might be connected, potentially. Connect it to pin 10 on the PLCC. There we go. That is ostensibly the address lines from the NES bus to the PLCC, to the floppy drive controller. So I think it's just data now. I think that's all I need to do. Where are the data pins? Where are the data pins? Are they the DB pins? DB0, DB1, DB2, DB3? Oh, that's right. And they just continue around that side of the chip, which, I mean, I guess that tracks, because that's where I was desoldering things. Hi, Lawless! Uh, let me read a little bit of chat because I didn't really keep up with it, and then we'll do these data lines. So Francois says, I guess it's more customary to French IRC channels, re as in re bonjour, hello again. That makes sense. I think the same, because I don't see it on most other channels, but on there's a private mud chat that I haven't been to in far too long. I never have time lately, but where they always tell me re whenever I log back in, so I always wondered. Now I know. By the way, Polko Mandy maintains a 1X branch of Kentucky before they dropped retro machine support. They dropped retro machine support? I don't follow Kentucky. I'm just like aware of Kentucky. Like, I have read for many years of Kentucky on Wiki, but I don't keep up with it. So that strikes me as insane. I thought the whole point of Kentucky was supporting like the C64 and stuff. Werewolf in the pin counting on PCCs. Cliff Cheney. Beep. Beep. Francois Rival says SMD smiley face. SMD isn't so bad. I did SMD for Boodly Doodly Doo, the VAX keyboard and mouse interface thing. And that was fun. I had never done that before, but I used low temp solder paste, and it was actually pretty easy to work with. I was pleased. Anyway, I said hi to Wallace, and Werewolf said maybe try with only D0 first. Try with only D0 first. Werewolf, you always suggest the correct things, and yet always the things that I'm not gonna do. Of course, I'm not gonna do that. I'm gonna let fly with 8 data pins and fly too close to the sun. So what I do think I will do for starters here, though, is just not keep my logic for the read and write lines set to always not set to any, always disabled, and having the chip select line the way it is probably fine. And then just make sure it still runs after I connect this chip up to the data bus, because it shouldn't be doing anything to the data bus if it's not got anything asserted, but that's a thing we will have to test. Okay, so where are my data pins on the EEPROM? They are over in a place. They start at pin 13 on the mask ROM, which is down here, 16, 15, 14, 13. Yeah, right next to the address pins. That would make sense. And now I try and do the thing where I try not to desolder the wires that are already going to the ROM. And also, try not to have any shorts. Also would be pretty good. Okay, so this was 9, and I think the counting this was 10, and I think the counting continues. 11, and on the floppy drive, I'm not going to keep swapping back and forth, I will just describe it. On the floppy drive controller, 11 is DB0. So, 10, 11. Okay, connected. That's D0. D1. So that on the PLCC that skips over a ground, which that will help me confirm my counting, so yeah. 10, 11, 12 is ground. Cool, yep. And then 13 is data 1. And I also know data 1 is just the next one down on the eeprom pluggity-doo. So I think that is, well, the last one was 13, right? So 16, 15, 14. 16, 15, 14. Just tidying up some wires, because they've kind of gotten all over the place. Well, not all over the place, but they've gotten a little hard to follow, because a bunch of them are pretty stacked on each other. Okay. 14. And yes, I just cleaned my tweezers on the solder Brillo. It's like the soldering equivalent of blowing on your ice cream to cool it down. Okay. D1 was 13. Yes. Okay, we are a quarter of the way done with the data bus. This is why 8-bit machines are nice. Can you imagine when I'm going to have to build, like someone is making me, like it's my job, when we get to the Genesis and I'm going to be doing 16-bit bus, yeesh, I say, where you double the work for every single bus connection that you need to make. Not great. Also, the thing about this kind of like dense PLCC solder work is it gets very 3D. It doesn't come across on camera, but you have to start like putting wires over other wires. Yeah. Anyway, that was D1. Let's do D2. How about? That would be 15. Then it goes around the bend. 16 is ground. Shit. I have desoldered the wire that was there. Good fucking job. Soldering is not fiddly at all up until the moment where it is extremely fiddly. That moment is now. But I got it reattached, so woo! Okay. That is D2, and D2 on the PLCC is the one right next to D1, and that was D1, D2. Oh, also, I will say, speaking of, you know, whether it's fun working with PLCCs in this way or not, try logic probing a PLCC. I'll wait. I mean, I'm sure there are special, specific pieces of hardware they make for doing that, but not something I have. Alright, that is D2. sure it's not weird. Yes, it is pin 17, so it's just the next one on the adjacent side of this connector. How long have I been going? What time is it? 2.5 hours. 2.5 hours. I might... Let's see how far I get with this. We'll see if I can read some... Well, we'll see if this works with some bullshit hooked up to the data bus. And then maybe try and get reading floppy controller registers, see if we can do that. And maybe make that the end of this stream, so I can go eat dinner with my wife and come back nice and early for the second half, where we, you know, if that all works, see about doing writes and see about writing software. Kinda doubt things will work out that cleanly. I mean, this is, I'm gonna plug it in, it's gonna be like, I don't know how to do anything, and all the bus, there's crazy bus contention, and the timing all sucks. But maybe we'll get lucky. Maybe. Who knows? Alright, so that was VCC, or VSS, ground. VSS, data pin 1, data pin 2, data pin 3. Right next to a very meltable insulation ground wire. So let me try and not melt that and bridge this to ground. Okay, hopefully that is not what I just did. All right, that was 3. Are we halfway through? Yeah, we're halfway through. Okay, 4 is next one up. Okay, yeah. D2. D1, ground, D2, no, D0, ground, D1, D2, D3, yes. Another ground, yep, and then D4. That didn't melt the insulation on the exact same thing that I was worried about on the last one. And bridge that to ground. Hopefully. Hopefully not. That was D4. D5 is the next one up. Making sure I'm not going crazy. Let's see. Was on the Mario connector deal. It is D0, D1, D2, D3, D4, D5. Cool. D3, D4, D5. And D5 was on the other side of this VCC pin. Yes, ground DB4, VCC DB5. Ground DB4, VCC DB5. It matches. D5. We are 3/4 of the way there. 2 more. Here goes D6. D3, D4, D5, D6, 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 D6. And that's the one directly next to D5, right? Yes, it is right next to it. So, VCC, D5, D6. I got a copyright strike on the video where it was my band, the video from last night where it was my band playing my band's music. And covers, but I mean, really? You think I'll get a copyright strike for humming the tune of The Wizard of Oz with lyrics about the data bus? Who can say? I don't even think people at YouTube can say. It's out of their control now. D6! One more! One more to go! D7, that's it. And then we can plug this in and see all the wonderful ways in which it does not work. Alright, D3, D4, D5, D6, D7. And where is D7? It is on the other side of a ground. Right, D6, ground, D7. Lovely. Yes, D6, ground, D7. Done. Done. Okay, so theoretically, I should just be able to plug this sucker back in. And I didn't change anything about, well, actually, maybe, well, let's plug it in, see what happens. And if it does weird things, then I will disable chip select entirely on the, or wait, no, it shouldn't matter, because chip select shouldn't be asserted on the floppy disk controller. Well, it will be, but it shouldn't be selected before we start hitting that inner test loop. We should not be accessing that memory prior to that, so chip select for that should never go high until then. And then at that point, if everything is, well, no, I was going to say if everything is wired up correctly, then we should just be reading from some register, whatever the 0th register is on that chip, but we won't be because I'm not asserting read or write right now. So this should hopefully just boot up and show us to the left and should be fine. Should be fine. Should be fine. If things are not screwed up too bad. Ugh. I mean, you know, I haven't really done too much to screw this up, really, for all of that soldering, but that indicates that, like, I didn't, like, bridge anything on the data bus or the address bus doing that, so that's good. That's quite good. To the left, to the left. You think I'll get a copyright strike for that? Alright, let me look at chat a little bit, and then we will edit some gal code to try and generate a read assert signal. I guess just whenever chip select happens, we're not going to do any writes to the thing yet, so we'll just make the gal logic work in such a way that we always assert a read. I guess we'll just make the read signal the delayed floppy disk chip select signal. That should be all we need to do, right? And we'll see if we can read some registers. Anyway, chat, yes. Let me scroll up a touch. Ooh, interesting. Okay. So Francois said, the Kentucky author did his PhD on sensor networks and he used it as an OS for sensor nodes, so they refocused. Oh, I found a website mentioning an NES port without network. I will have to look that up at some point. Someday I will have to play with Kentucky. I really do need to play with it. Lala said, where are we at right now? You probably sent that quite a while ago, but basically, I don't know if, at what point you really came in here. I said hi, and I don't remember when that was. But so these are basically the pins from the MapROM. I keep saying MapROM, or I keep wanting to say MapROM. That's, I think, the first time I've actually said it. But that's not a word. The mask ROM. So instead of having the adapter on there, they're just running out these wires. I don't know if you already knew that, and they're coming in here. And so this running through here is just the exact same thing as the adapter that we had before. But now I have attached a GAL here. This card already had this floppy drive controller chip on it. Should be pretty much wired up to the clock and the plug for the floppy drive correctly. I already did that ages and ages and ages ago. And I think I did everything except for the computer side, like data bus and address bus stuff, which I just did. So we connected, I just finished connecting the 8 bits of the data bus from this connector over to here. So now this is on the data bus. It's not doing anything yet, but it's connected to it. I connected, this takes 3 address lines because there are several registers on board, and those are just connected directly to the CPU's low 3 address lines. And then this GAL is currently not doing much. It is, there's a chip select line on here for the EEPROM that appears to be working okay, and it is set up in such a way so that the EEPROM only gets selected when we are reading or writing to the highest area, I guess. I can't remember how many, this is a 200, no. Maybe this is a 32K ROM. Anyway, you can fit 4 of these inside of the, like, capacity-wise, you could fit 4 of these inside of the mask ROM that actually goes to this card. So this is now, this GAL selects this chip now. This chip used to just kind of always be selected when the map ROM was selected, but now this is only set up to only select it when addressing the highest, that 4th mapping of this chip, which is exactly the area in which we've been executing code out of. So this is effectively mapped in at the same spot that it was. We just kind of turned off the rest of the mirrors of this chip in the mask ROM virtual paged memory space, so that we have the rest of the area to map things in, like this guy. Then I updated the MMC3 so that this, we checked the chip select for this was programmed up and working properly, and the MMC3, I wrote code that is configured properly now, so this, the chip select for the floppy disk controller gets selected when we read from, or when we access A1000, and I checked, that is working. Theoretically, it's getting selected right now. But we also connected the read and write control lines between the gal and this, but right now they are just set to always be deasserted. So this is getting chip selected theoretically right now in a loop, but well, not right now. Now it is, but not putting anything on the bus. So how's about we make it put something on the bus? Anyway, sorry, that was just a decent. There was a lot to catch up on, so I figured I would use that message from Lawless to go to the trouble of re-describing what's going on. Derek says, once I finally did SMD, now I never want to go back, or at least for anything I want to look professional. Of course, that means breadboards filled with too many SMD breakout adapters when tinkering. I mean, not that, because you are obviously making like more productizable things. My things tend to be one-offs, so like I never get past this phase. But like I very much liked my process with the VAX keyboard and mouse and monitor hooker-upper doodad, because that was fun because I did the design with through-hole parts and point-to-point wiring so that I could really mess with it. Actually, I did the original one with jumper wires, so not even any soldering, and a breadboard. And then took it to an SMD finished product, and that felt good. That felt quite good. Wereworm. Not only look professional, but drilling a million holes in your PCB gets old fast and ruins your drill bit. Yup. I tried. I had a great interest in late high school in trying to make my own PCBs, because that was kind of a thing at the time. Like, half of Instructables was, in like 2007, 2008, was like, how to etch your own PCB. It really was, like, half of Instructables. And that is the thing, is drilling holes sucks. And I snapped a bunch of bits, and then I finally said, nah, not gonna do it. Francois Reval says, how about wire wrap? Haven't tried, actually. I was talking about wire wrap the other day. This is this little stripper that I've been using, this little brass thing, is from a wire wrap tool. This is wire wrap wire. I find this way easier. It's hard to find. I think in Europe it's still easier to find wire wrap parts, is my impression. But over here, like even just like wire wrap sockets in and of themselves are expensive as hell, and kind of not super available. Oh yeah, Wereworm said, me neither. Sockets are expensive as hell and rare, like I just said. Wereworm said, if you like SMD, Google Elm Chang extreme wiring on the prototyping board. Well, I'm gonna have to do that too, just for the pictures. I like me a good electronic spaghetti picture. Wereworm said, there should be a tool that works like the bonding machine, scaled up to work with magnet wire. Bonding machines are friggin' cool. I like them. They're fun to watch. Francois says, I wonder if something like what a sewing machine does couldn't be used. I mean, I think the bonding machines, they're more or less like a pick and place, like they have an XY thing, just like any other a plotter or a 3D printer or whatnot, and then they just kind of have a wire dispenser and the ability to dump a shit ton of current through them. Because I do wonder about that, because how does I don't know. I want to know more about the physics in general of, like spot welding. Because I think pretty much IC bond wires are basically spot welded to the pads. And so that is pretty much just them dumping a shit ton of current through the wire and like melting the end of it and melting the pad a little bit so that they squoosh into each other and bond. But how does that not destroy the chip? But also, like, when you are doing that kind of welding, like on a larger scale, you don't electrocute yourself when you're doing that. So obviously there is something about the current really just stays right there. So these are things that I don't get about it that I would like to understand better. Santiago says, cool, so what is the end goal of the floppy disk? Using a real disk drive or something like the GoTech? Oh no, we're gonna attach a real floppy drive to this thing. Francois said, search Hitman Kentucky. That will go on my list. Santiago said, when I started making my own retro single-board computers and such, I switched really fast to a pre-made PCB from cheap sources. Hand-wiring a Z80 on a universal PCB is absolutely hell. Yep. That would be the reasonable thing to do, but I enjoy hand-wiring is the only reason I'm doing it. I'm not doing it because it's better or anything. I just like it. Wareham said, bonding is done with ultrasonic, I believe. Ah, okay. Interesting. Interesting. I'll have to do more research. Okay, so I guess making the read line read. Let me pull the PLCC back out of this thing. And I know this is silly, but I'm going to pull this out, and then I'm going to turn the thing on, and it should shit itself. And I'm just going to do that for fun, just to prove that the PLCC is, or the GAL is doing things. Yeah, there we go. The GAL is now intrinsic to the operation of this device. Okay, so like I said, I'm going to make this only do reads right now, just for starters. And let me switch to my computer screen. So right now these are hardwired to always be on, so write and read will never actually be asserted on this thing. And what I will do is I am actually going to make the read input FDC CEB delay. And that was, if you didn't see it earlier, so what we found a minute ago looking at the logic analyzer is it seems like from the input to output time on the GAL is something like 10 or 20 nanoseconds. And on the timing diagram for the floppy disk controller, you must at minimum assert the read or write signal 5 nanoseconds or more after you chip enable the chip. So I'm using the GAL itself to insert a delay. So what's happening is the chip select for the floppy drive comes out pin pin 18 here, and that is actually wired not only, let me make sure I'm not crazy. Yeah, it's wired both to the chip enable on the floppy disk controller IC, and it also goes into pin 5, and that's where it gets called floppy drive CEB delay. So theoretically, what's going into pin 5 should be delayed by 10 to 20 nanoseconds relative to the floppy drive chip enable signal. And then we're just going to feed that right to the read pin on the thing, so that it should just be a slightly delayed version of chip enable, so that we can match that at least 5 nanoseconds rule that they have in the datasheet. One error. Am I missing a semicolon? Oh, wait. Invalid syntax. Didn't I already compile this? Uh-oh. True? Shoot. Wait. An error is encountered. Is it something silly like .t dot? Nope. Is it just T? Two warnings. Oh no. Nope, it thinks it's variable. Huh. How is that not acceptable? Okay. Okay, we're looking in the syntax. Kupel Programmer's Reference Guide. How do I declare... Firstly, that's kind of shitty because that means that I guess I never compiled this version of it. Oh, Microsoft Edge. I didn't intend to use you. Ugh. I mean, Edge isn't that bad. It's just the idea of it, you know? Anyway. Kupel Programmer's Reference Guide. Where are you? Hello? Hello? I'm clicking on the edge button. There's an edge window somewhere. And, it's not on any of my monitors. Thanks, Edge. Perfect. Oh, okay. Help not included. Excellent. That's super good. Oh, and now I accidentally opened the Windows store. I'm just having a great time. Let's just look up Kuppel syntax. Kuppel Programmer's Reference Guide. Here you go. I just want to know what a static true value is. Indexed variables, reserved words and symbols. Are any of these true? Uh-huh. Uh-huh. Uh-huh, no. Numbers. Oh, do you think I have to specify this as a 1-bit binary value? Well, I guess I can. I guess I can do that. That would work. So is it this? Is that what I was reading? Cool, one warning. Seems fine to me. Cool. Let's burn it. Back to 16v8. 8v16? ATF 8v16? No. 16v8. B. Yes. There we are. There we are. Let us load the JED file for the map. CPLD, give it the old program. Shove it back in. Let's just shove it back in and see if it doesn't break anything still. And then I will maybe write some NES code to try reading it and print something. I should probably just go ahead and at this time implement some converted number to hex code, because that's real easy to implement and would be helpful. So anyway, that's programmed. Let's get it back in the thing. Make sure it didn't break everything. Still works. That doesn't mean much, but it still works. Yay. Okay, let's print something. So let me look back at the data sheet, and what I need to know is, what are the registers? What are the registers, dear floppy drive controller? What are the registers? Hey, right here. So I will read more about these later, but the one at 0 is status register A. And I think that's the kind of, or maybe main status register might be useful, because I'm figuring reading from one of the status registers, I should get, you know, pins that make, or, you know, values coming in that make some sense status-wise for the floppy controller. And that would indicate to me that I am actually accessing the thing in a way. So I think let's just read from the 0th one, as we're already doing, but then print out what we're actually getting and see if it's absolute garbage or not. Yeah, so let's Control F SRA in this document and look at the documentation for that thing. Here we go, status register A. PS2 mode. I don't think I have this configured in PS2 mode. There's like a pin Let's actually look up PS2 mode really quick just to double check whether I have this thing in PS2 mode or how you set that up. PS2 mode. Wait. I think it's on a pinout. I think there is a pin that, like, you ground it for I would like you to operate as the old style chip, or I would like you to operate in PS2 mode. Let me scan. And if it's not obvious here, then I can look in the table of pins. Okay, I'm not immediately seeing it, so let's go ahead and look at the table O pin names again and see if there's an obvious one. Reset, chip select, address, data bus, read write, DMA, request acknowledge, terminal count, interrupt, crystal, identity. Okay. Upon hardware reset, this input selects between 3 interface modes along with the MFM pin. After reset, this input selects... Oh, there's another thing. Is that right? Right. There's probably a super hack that I can do here, but the... I need to generate a reset signal. Which, I guess if I was thinking about this whole complex thing, but if I'm just gonna... I'm gonna need to run some pins from not the map-ROM socket. For example, I will need the CPU clock. I will need the CPU read-write pin. So I might as well also run over the... if there is a reset signal, which I'm pretty sure there is, and just run that straight to the floppy disk controller. Let's just do that. Yes, which actually is a thing that I probably am going to need to do here. F it, let's write some code anyway, and then we probably will get garbage either way because this hasn't been reset. Yeah, cool. Anyway, regardless, moving past that, back to this identity thing. The MFM pin is also sampled at reset and then becomes an output, blah, 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 blah. So PS2 mode is if the ident pin is... Oh, okay. So there's PS2 mode and Model 30 mode. I think Model 30 mode is the... Yeah, PS2 mode is like classic PC mode. Model 30 mode is like the special crazy 2.8 meg floppy version, I think. Yeah. Yes. Okay, so PS2 mode is standard PC mode. Or wait. Do I want AT mode? I don't know. I guess it doesn't really matter. I just need to know what mode it is in. So let's check which pin is ident. Ident is pin 27. And then I just need to look at what the heck I have. I do have it wired too. Ident is down here. Let's see. Let's work this out. Ident is... Where's my... Okay, so this is upside down firstly. This pin is ident. Right there. And on this side... Wait, is it? Yes. It's the one across from the bevel. Yes. Okay. And what is near there? What is near there? Okay, I'm just gonna have to count. So this is going around this way. What? Oh, no, it's on this corner. Wow. How did I do that? My brains. Okay, so whatever. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 24, 25, 26, 27. Okay, cool. I didn't hook that up to anything yet. That's good. That's fine. Okay. I guess let's put it in PS2 mode. Let me just recount to make sure. In fact, I did not connect anything to that pin. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 20... Wait. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 25, 26, 27. I see. Okay, that is connected to 5 volts, so that is pulled up to 1. I was wrong. It is not connected to anything. It is pulled up to 1. What does that mean for me? If it is pulled up to 1... Okay, and I don't think I have it, so I guess I have it in AT mode. Good to know. Okay, so this is wired up for AT mode. Back to my registers. So, I guess let's look at status register A again, and SRA. Bloody blue. Oh, I see. They have a separate section on each mode for them. So this is PS2 mode. This is Model 30 mode. Is there no AT mode? Oh, you're not looking at my screen. So status register A. So it's got it listed in PS2 mode. It's got it listed in Model 30 mode. And not in AT mode. Okay, hold up. This register is read-only. This is for register B. Not part of the PS2 register set, not accessible in AT mode. I see. So probably the same here. This register is read-only, blah, blah, blah. This register is part of the register set, and I suppose that's supposed to say the PS2 register set. Not accessible in PCAT mode. Okay, so reading those two, can't do it. Status register B. Also only PS2 and that. But then there was the main status register. Okay. And main status register was somewhere. Where is that mapped? Main status register is at address. That's going to be A. What is this? A4? Yeah, 1, 2, 4. A4. So let us, instead of reading from, right now we're reading from A1000, let's read from A1004. But here's the deal. I would really like to see what's actually in there. So I'm going to do this the cheap way for starters. I am going to make a loop, and I'm just going to shift it out and print the bytes, or print the bits, instead of just printing hex. Is that okay? Sure. We'll write some hex code in a minute, but let's just dump the bits. And then see if it's garbage. See if it's at all reasonable garbage. See if it needs a reset, or see if it is just absolute not working at all. We're gonna find out. So let's call this bit shift loop, and we will start by let's dash A and Y, or I guess we can push it. Let's push A, because I already know that we're going to be printing characters, and those are going to budge up our X and Y registers. So take the A value, push it, and then let's AND it with... okay, I have to think about this. So I want to print on the screen with the most significant bit to the left. So I want to AND with 80. Right? Yes, and then we will have to shift to the left. And then branch if it is 0 to bit is 0. Otherwise, we'll print, we will load a 1, and then jump to subroutine, printer, and then I guess, oh, you know what we're gonna need to do is we're gonna need to do the old countdown. So let us firstly, we're not really going to want to do this in a loop. We're going to want to read this one time and then hang. So that's kind of fine because we will just fall through to halt loop, which is the keyboard stuff. And get rid of this stuff. Bit is 0 is just going to do... And I realize this section is not done yet. Just don't worry about it. Load A. Oh. Probably need a literal in front of them. So if it was 0, then we load a 0. And then we JSR printer. Before that, though, so for both of these, I think I'm going to use load X 8, yeah. Load X literal 8 and do. I guess you know what we can do. We can just clear carry, branch carry clear, print bit down here, print bit. And for print bit, actually, you know I hate doing this, but we will just do I need to take X and I need to stash it for a sec. So we will also push that. Actually, also here. We should load A and then push it. And then actually at the beginning here, we will pull it at the top of the loop. Anyway, and then I guess we need to push it again, really. Which doesn't affect anything, so we'll push it right after doing that. And that doesn't affect any of the flags, as far as I remember. And then let's transfer X to A and push it. Does that make sense to do here? Sure. Let's preserve X here, but we'll also need to do it here. Transfer X into A. Preserve it. So now on the stack we will have the value of A and the value of X. Yeah. Anyway, so here's the part where we will print the character. And once we are done printing the character, let us pull that X value into A and then transfer A back into X again. Then decrement X, and if it is 0, let's jump to print FDC reg done, which is going to be here, where we will move on to just doing keyboard bit again. Otherwise, if x did not hit 0, let us push x, no, but we'll just keep x and x, because it's when we come back around on the loop that we will stash it again. But now we will pull A again, and let's see what my shift options are in a 6502. 6502. Sit. 6502 instruction set. Shift. Arithmetic shift left. Cool, that's the one I want. ASL. ASL. And then push A back. Clear carry. And branch carry clear to bit shift loop. And there, that should kind of work maybe. So it's gonna reload. Let's double check. So we're gonna read that status register. We are going to stash it onto the stack. Then we load 8 into X. We pull the A value back off the stack. We check the high bit. We push it back. If the high bit was 0, we jump down here. We stash the current value of X, and we print a 0. If it was not 0, we stash the value of X. Oh, and yeah, we push the value of X onto the stack. We load a 1, and we jump on over to the print bit thing, which is where this would fall through to if we were in this leg of things. We call the print character subroutine, then we pull X back off the stack. We put it back into X. We decrement it. If it was 0, then we jump all the way down here and exit that whole loop. Otherwise, we pull A back off the stack. We shift it left by 1 position. We push it back onto the stack. Then we clear carry and jump back to the beginning of the bit shift loop. Does that seem reasonable? Oh, I bet that's this right here. Look at chat. Jacob just says, chips. Francois says, what is this clickodrome? Oh, have you not heard me typing this far? I have oh, I've already forgot. Text Shinobi. It's okay. Lol says, Opera GX is a decent browser and has some cool features. I've never played with Opera, really. I've never been an Opera user. Nico said, congrats, it still works, back when I re-ran it. Will there be an NES printer made as well? Only time will tell. Wareroom said, yeah, I think I saw status register not available for AT mode. Yeah. Lola said, kind of funny using Intel parts. It's because I already know how to use this floppy controller, and it's the one for PCs. So that's the one I bought off of eBay. Percher, says Nico. Wareroom said, make a print bin sub and just unroll it. No loop needed. Yeah, again, the Wareworm probably right. I will, at the very least, probably go shove it over into a subroutine at some point, because it's useful code. Francois said, oh no, I was referring to the PLD GUI. I have a Model M myself. I have never used a Model M. I don't think I would like clicky switches. Not to besmirch the Model M. That's not to say I'd like to think it's a bad keyboard or whatever. I just, I don't think I'd like it. I really had no interest in mechanical keyboards until I got a Mac that came with a Apple Extended Keyboard 2, and that has Alps salmon switches in it. I think it's salmons. And they're a linear switch that I don't really know much about it, except that apparently people really like them, and I do. And that's like one of the best keyboards I've ever used. So I use browns on pretty much everything, and I like them. But I'm not like a big keyboard person. Okay, let's run this in the emulator really quick. Just to it should do something, and it should print 8 bits. Or not. Or it will just print zeros until the sun explodes. Fascinating. Why would that happen? It's gotta be because of this X situation, right? Let's trace X here. So we load a literal 8 into it here. Not touched, not touched, not touched. Not touched, not touched. Oh. We put it in A, then we push it. Okay. So at this point, ignoring everything else, it's still 8, and we just put it on the stack. So there should be an 8 on the stack. And then same here. It was 8. We put it in. Oh. That would do it. We were putting A in X, not X in A, in that particular location. That would cause problems. I'm glad I checked this before writing it to the hardware. Yay! Okay. Why it wrote a... Oh, it wrote a semicolon because of the keyboard. The routine kicked in there. Lovely, lovely. 1, 2, 3, 4, 5, 6, 7, 8. Cool. Let's do a... We can do a check on here. That is actually going to be really useful. Let us look at RAM, or let us look at actually. I mean, I guess NES memory is fine. I want to find a byte in here somewhere that has a nice recognizable value, and then print it. Sure, at E300 on the cartridge we have 3B. Let's print 3B. So instead of loading from A1004, we will load from E300 just to check. And that should be 3B. A1004, where was that? Right here. Make that a comment really quick, and we will instead load from, was it E300? I've already forgotten, and I closed that window. What a genius. Can we do a jump to? Go to address. So E300? It was! My brain is good. I just gotta trust it. Okay, so there's our change. We know there is a 3B there, so it better print a 3B. And if it does, then we can trust it pretty okay. Open. Nope, that's just zeros. Neato burrito. Did I actually build this? Did I actually save it? Did I actually build it? Let's try one more time. Just to make sure. Nope, it's printing all zeros. Interesting. Let's debug it really quick. So E300. Something's got to be off, because this is... Oh no. Huh. So this is E300, it's got a 3B there. Okay. Seems fine. What is that stuff? What even is that stuff? Oh, that might be, all of those zeros might be part of one of my tables. Oh, plus the alignment stuff, probably. That's probably what's up there. Anyway, still, that should be loading a 3B. Let's find my actual code here. Oh, yeah, E300 was where I started my key table. That's what that was. Okay. Oh, actually, let's see. Do-do-do-do-do. 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 I guess I'm looking for E300. Here we go. Load A, E300. Very good. Let's just put a break at E150 and watch this whole loop. E150 on execute. Coolio. Reset. Alright. So, it has in fact loaded 3B. Cool. Push 3B onto the stack. Cool. Load 8 into X. Cool. And what's in A with 8, 0. That makes sense. And then push that on the stack. Wait. Yes, no, that's fine. I pulled the 3B off, then I pushed this back. Oh! Fuck balls. That's why. Because it clears that first time. I was even thinking of this when I was about to write the code, and then I just forgot about it completely. Right, we don't want to write the ANDed value. We want to write the old value. So we pull A, and then let's stash it in Y. Transfer AY. Yep. And then right. Then it gets silly because we need to push Y without upsetting A. Or wait, also without upsetting the output of this. So actually, well, we're not really doing anything else with Y. The only thing that happens is when we finally print things, Y will get corrupted. So that's fine. It can hang out in here, hang out in here, hang out in here. Annoyingly, now X will get pushed before the value of A. Well, unless we just TYA. Again, I hate doing this twice in each branch, but move Y back into A, and then push it. And same thing down here. Move Y back into A to put the old value of A before it was ANDed back into A, and then push it. I'm going to get rid of that breakpoint. I feel pretty good about this. Trying to fly into my mouth. I'm not gonna have it, you hear? Okay, that's correct, right? 0, 0, 1, 1 is 3, and then 1, that's 8, 9, 10, 11. 8, 9, 8, B. And it was 3B, yep. Yes, it was. Yay! There you go. Cool. So this will probably not work over here, but let's change it back to 8004 and put it on the hardware and send it. And then, let's see. It's going for 3 hours and 30, and it's 6:01. So I will send it, we will see what it does, and then I think that's the end of Megastream 1 for the day. Let me review chat, and then we will do this moment of destiny. Okay, so there was Wereworms just on Roll It story, or comment. Cliff Cheney says, I have an HHKB silent and a Rama Works Kara with Novel Creams, also silent. Super cool. I just want to say this goes to the point of I am not actually really a keyboard person because none of that meant anything to me. I'm sorry. But I hope you enjoy the heck out of them. I really do. Wereworm said, I think a print hex would have been shorter, only 2 characters to print. Yeah, but you got to do the whole... there are more branches involved because you have to check, is it greater than this? Is it in this range? Then subtract the hex 0 value from it otherwise. I mean, it's not hard. It's probably about as difficult as this, but this is what I did. Nico said, 0000000 NES Basic 2022. Truly an inspirational quote. I can't add anything to that. Cliff Cheney said, I noticed the Shinobi 4. I actually have a new set of GMK ThinkPad style keycaps waiting for me in the US for my Kara. Yeah, I like the ThinkPad colors. And I like me a touch point. And so having a keyboard that has a touch point on it is cool, and especially for this desk, it actually works out really good. Not why I wanted it in the first place, but it works out great because then I save a bunch of space. But its touchpad is kind of it's both stiff and really touchy at the same time. It's not as good as like an actual ThinkPad touch point. Nico followed up with 000000000, followed by some dots and a face. NES Basic 2022. Wereworm said, why not pull A, push A, transfer A to X? My brain's too shot to answer that question right now. I'm not in the context anymore. Francois said, for my next ThinkPad, I got a T530 that I stuffed a T520 keyboard in because I can't stand the chiclets. Yeah. I got used to... I think I have a T530. I think that was my last laptop. I since upgraded to one of the new M1 MacBook Pros that I've been thoroughly enjoying, but I was disappointed by having a ThinkPad that had chiclet keys, or island keys, whatever you want to call them, but I got used to it. It's still a pretty good keyboard. But yeah, like the full IBM style keyboard will always be classic. Jacob says, does it have a file system thing? Like, can I type LS and see stuff? If you're asking me about this project, there isn't even a floppy drive connected yet, so that's a strong no, dog. Cliff Cheney says, yeah, I love keyboard hobby. I have a dead ThinkPad X200 I keep meaning to resurrect. You can't get away from ThinkPads. Nerds love ThinkPads. Francois says, I'm actually using an X230 tablet with an X220 keyboard right now. IBM's got us by the balls. And Nico said, at Jacob, right now the only thing you can type... Oh, yeah, he was responding. You can type is lol in all lowercase because all you have is zeros and ones. And Francois says, back to the chiclet deal, worst thing is not chiclet itself. It wasn't that bad, just that the layout is unbearable. I don't like any laptop keyboard layouts, period. I guess that's one thing that I do have a bit of a strong opinion on. Not because like I think about it too much, but especially like because the navigation keys are always different on every single laptop ever made, and I can't stand it. Whereas like any reasonable keyboard has the PC 104 layout and the navigation cluster is always the same. Yeah. Anyway, which is also one of the things that again, I'm not like a Vim super user, but it's a nice thing about Vim because then I don't have to, I just use the home row and I don't have to worry about the navigation cluster, and it works fine on the laptop and it works fine on the Text Shinobi, and everyone is happy. Anyway, let's do this thing. All right, change this back before I forget. Cool. Link it. Cool. Switch back to the EEPROM. Whoop. 29E010. There we go. Load NES. Basic.bin. A name that just gets funnier and funnier as we go. And stream for hours and hours and still not even coming close to starting on doing stuff with BASIC yet. Oh well, it's aspirational. Oh, I need to clear the check ID bit because for some reason that always fails. And let's just revel again in that sweet, sweet ZIF socket goodness. Boop. Boop. That's it. That's it. No prying. No nothing. And it's programmed. And let's just give this ZIF socket its due yet again. In it goes. Locked in. And it's done. Okay. Fingers crossed. I don't know what's going to happen, but whatever happens, happens, and then I'm done for a little bit. We got stuff. It doesn't look insane. Let's see if it looks the same every time. We still need to reset the damn thing, but it looks pretty consistent. Only 999,999 writes left on the chip. Yep, it's gonna burn out soon. Sometime in the next 1,000 years. Okay, so. Yeah. That looks right. Alright, let's see what the status register is actually supposed to have in it. And if there's anything that would, like, be... Well, let's just see. It might be total garbo without a reset, but it's worth looking anyway. And then we'll get back to it. Okay, so that was... I'll switch my screen in a second. That was main status register. Scroll, 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 scroll. Main status register. Okay. So let's revisit... Let's revisit what it says. So it is 101 and all zeros. So in the hardware reset state, this would be a 0, but we haven't reset it, so that's fine. But that is RQM, indicates that the host can transfer data if set to a 1. No access is permitted if set to a 0. Okay, that seems like something that could be 1 or 0. DIO indicates the direction of a data transfer once RQM is set. Non-DMA. This mode is selected in the specify command and will be set to 1 during the execution phase of a command. I think we really need to reset this thing, huh? And the rest of these are all zeros. Which, that seems... All of those being zeros seems decent, because if any of these would be 1... If any of these were 1, I would be concerned. Drive 0 busy, drive 1 0, and drive 1 busy, drive 2 busy, drive 3 busy, currently busy with a command is what those would be. So, I feel okay about this. Are there any other... I think all the other registers are like registers for transferring data and stuff. Oh my god. Why is this scrolling so chonkily? I promise you, it's not the streaming. It's really that bad. Let's see what else we have anyway. Data, digital input register. Yeah. No. Not a lot of other good stuff in here. Oh well. But, I mean... It's sending me the same thing every time. Yeah, I'm going to leave it here. I am doing a two-parter today. Part 2 will probably be a little short-ish because it's already 6, and then I want to... Like, I'm not going to stay up till 1 tonight again. That would be insane because I have work in the morning. But I will put in some hours. But we're getting something. So that's cool. And I don't think it's garbage. I don't think. Okay, maybe before I go, let's read an area of memory where there would be garbage and see if I get the same thing. Well, no, I don't know. Let's read from the digital input register, because I mean it is going to be garbage, but it should be different at least, unless that will show that it is in fact, if the value read here is different from the value read here, then we can be pretty confident it's actually managing to successfully read from that chip, and it's not just bus garbage. And let me just make sure that register, that register has to be available in AT mode, right? It's got to. Doodly 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 doo. Is it digital input register? Uh-oh. I don't remember anymore. It was the one at address 7. Address 7. Digital input register. 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 Please tell me that it is not. Okay, PCAT mode. Good. It's read only in all modes. Blah 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 blah. In PCAT mode, oh, interesting. In PCAT mode, only bit 7 is driven. All other bits remain tri-stated. Interesting. I don't know if there are pull-ups or pull-downs on this on the NES's bus. Like, there's got to be something like that. Surely. Well, anyway. It's there. We can use it. Let's do that. That was 8007. Write it. Build it. Turn this off. Pull out the chip. Put it in the programmer. Go to the XG Pro program. Load from basic.bin. Make sure the offset is right. Hit OK. Hit program. Hit program. Cool. Pull it back out of the programmer. Put it back in the hardware. Turn it on. Huh. Damn. Oh, I guess it is bus garbage. Damn it. Damn it. Okay. Well, when I get back, it's gonna be logic analyzer time. Because at least I can read the data bus just by clamping that clip onto that chip. And then we can sniff some, control signals off of this thing. Damn! It was good while it lasted. Okay, let's read chat, and then I'm going to get out of here, and then I'll see you guys in a couple hours. Jacob asked, what does to the left mean? So it goes back, firstly, obviously it's a reference to the left. But I originally wrote that string when I was trying to get character printing working, and it was to prove that carriage return worked, so I was going to print the string, I did print the string to the left, then did a carriage return, then printed another string that should have showed up to the left of it. And it did! But it's just been there because it's a thing now. Wereworm says, do you have a floppy emulator thingy? Maybe only working with 5 volts? No, I gotta use a real floppy. I don't have a GoTech or anything. Zelsa said, 12 watchers? You're moving up in the world. Congrats. I don't actually know how many people are watching me at any given time. I don't keep that one up, so good to know. Thanks for watching, guys. Yeah, Francois says the OS Dev Wiki has a whole page about the FDC. Very aware. And I don't know if you were watching at the time. I already pulled up the OS Dev wiki earlier. But yes, I have spent much time on OS Dev. Francois says, reminds me, I have to fix the floppy driver for Haiku to use the ACPI table for probing. You play with Haiku? Like, as in the actual code base? That sounds fun. A project that's in the back of my head, but that I will never have time for, because I'm too busy doing other things, is I believe there is already a experimental ARM fork of Haiku. How great would it be? This is speaking as somebody who has an M1 MacBook. To take the work done for Asahi Linux and merge that. Using the word merge sounds weird because I feel like that makes it sound like it would be so easy. But you know what I mean. Like, it would do the manual work of incorporating those changes into the Haiku ARM branch and get... makes it sound like it would be so easy. But to get Haiku running on M1 is all I'm getting at. Sounds like it would be... I think that would be super, super neat. Francois says, yeah, worked on ports to PPC, M68K. That is so cool. Seriously, working on an actual big-ish open source code base is something that I haven't really done, and I've always wanted to. And when I was a teenager, it was way too scary, and I couldn't read code well enough to like understand how shit fit together. And now that I am at that point, I don't know what I would contribute to, except for like this idea, but I don't have the time, and I don't have the time, so it's a real bummer. Because obviously my interest is like low-level programming, and I'd love to do like systems programming stuff, which I have never done professionally. But yeah. So frickin' awesome, Francois. Zelsa said also neat, and yeah, it's neat as hell. Francois says, the ARM port is advancing, by the way. Maybe someday on M1. Who knows? Yeah, I bet someone will get to it long before I ever will. Because I will never do it. Anyway, as I already said several times, that's the end of this segment of the Mega Stream. I appreciate it. I appreciate all y'all. This has continued to be fun. Let's come back in a couple hours, and I will do my best to try and reset this chip and actually use the logic analyzer to make sure that it is putting shit on the bus and stuff. That's all for now. Bye. Wait, no, sorry. Gotta do the right one. See ya. Love ya. Bye-bye.